Like it seems good. Anyway, I got it like. That's the whole thing. Okay, see, that's what that. Yeah, I'm sorry. It says. No, because the first time but I'm not here
All right. What we're about to learn, in my opinion, is the most important thing you need to know to be a good MRI tech. If you get this stuff down, I mean, outside of patient care, that's a very important aspect as well. But as far as being able to utilize your machine and produce quality images and make changes that the radiologist requests, and, just understanding all of this stuff is gonna make you a really, really good tech. And sky's the limit there. If you understand this stuff really well, you can work with a vendor, do applications training. You'll be the lead tech, you're the guy they come to, or girl that they come to make the protocols look good, right? We want our protocols to be fast, look good. We want to have certain type of contrast, make it happen for me. Got it. Go in there and make all these adjustments. You're gonna have to make changes too. Fortunately, everyone gets scared about this, thinks they have to add all these parameters in every time. Fortunately, you don't have to do that anymore. Back in the day you did, but now everything is saved on the computer. So the protocol's already built, right? But there can be things that make you have to change it. The radiologist might not like the way it's built. You might have to switch out and use a different coil because the coil you usually use is broken. The coil that the protocol was built for isn't working, right? And we're gonna find out today, coils are a big factor in your signal to noise ratio. So if we change the coil, things might change. Patient might not produce the same type of quality because they're moving or something's going on. You might have to make adjustments. You might have to do things faster than you normally would because you need to get the person out of there, but you got to get certain pictures before they move, right? So parameters and trade-offs, I think in your book, it's called protocol optimization. Same thing. We're going over the same material. But yes, in my opinion, this was fun too. This is what I got into this. I liked it. It's definitely helped me in my career understanding this stuff really well. There's gonna be a lot of questions on your credentialing exam about this. So if you don't care about it, other than passing your test, just at least know that you're gonna need to know this really well to pass, not only this class, but your credentialing exam. But hopefully you'll want to know this in and out so that you can be the best tech you can possibly be. So the reason I bring this up, and this is in Canvas as well, if you go to week 6, you'll see this up there. I just wanted to kind of go through it real quick. This is a graphic user interface of an old GE scanner, right? So you're gonna see this on the screen. It's much more modernized now, but I like this because it's showing all the parameters that we're gonna go over all on one page. Now everything's kind of tucked away behind tabs. They made it more modern. Makes sense what they did because there's a lot more options and stuff as opposed to like clicking on different things and pulling up other sets of parameters. It's all kind of laid out in between tabs, but I like to pull up this old one because you're going to see all these different parameters that are on here. All right, so ones we're going to talk about today, I'll pull this back and forth, but you see, got a TE right here that we can change, right? TR is a function of the flip angle in this type of pulse sequence that we're running here. It's a gradient echo sequence. We can tell it's a 60-degree flip angle, right? So the TR is a function of the flip angle. Remember, TR and flip angle determine your T1 weighting, right? So it's not letting you prescribe the TR, but you can, because you see it's grayed out, but in other sequences, you would prescribe the TR. Got your flip angle, something called bandwidth that we're going to talk about today. But you can see we can enter that in, right? Field of view, FOV, that's what it stands for. Field of view, specifically frequency field of view is what we're going to be calling it or referring to it as, and that's what you're going to see on more modern systems. Slice thickness, we're talking about that as well. Frequency and phase matrix, these are your matrices. Your phase frequency direction. Next is an important one that we're going to talk about. Phase field of view, we'll get into that next week. It's the last couple of slides in this. I'm gonna save that for next week. We won't test you on it. It's just because there's all the stuff's your brain's gonna hurt at that point. I don't want to force that last thing in at the last second. So anyway, I show you this because look, all those things you can change and adjust, right? And I'll keep going back to this when we're speaking about each one of these parameters to kind of show you where it is, and we can do some exercises with it as well. You can also see up in here, we won't talk about this, but you can see patient position. Where are they going in feet first, head first? The coil that you're using, right? Series description, 2D versus 3D, planes, the pulse sequence type. Patient session number, patient ID, all that good stuff. So let's get into it. All right, parameters and trade-offs, protocol optimization like it is in your book. So what are the protocol? What we need to know before we know how to optimize it, right? So protocol, different pulse sequences within one exam that contain a variety of parameters. So a pulse sequence, you run several different pulse sequences. Typically, they only have one weighting, right? So I might run a T2 spin echo, sagittal. I run a T1 axial spin echo, proton density gradient echo, right? All of those are different pulse sequences that we run. So a protocol is a set of different pulse sequences that we are going to run on a particular body part, right? And each one of those pulse sequences has a set of parameters, which we will discuss. All the parameters that we discuss are going to be these ones down here. An average MRI protocol contains around 5 to 10 pulse sequences in different planes and different contrast weightings, right? We have sagittal, coronal, axial. Each of those planes is diagnostic in a different anatomy, right? So sagittal is not typically diagnostic. If you're looking at the IACs, it's coronal and axial. If you're looking at the pituitary, your axial is typically not diagnostic. It's going to be coronal and sagittal. So that's why we have all these different planes that we utilize. The parameters that we will cover today are TR, which we've already been talking about, PE, flip angle, next. We've talked about these three, which are contrast parameters, but there's trade-offs to getting contrast that we will talk about. Next, receive bandwidth, field of view, frequency field of view. We'll talk about phase field of view, but we'll talk about that next week.
And then matrix, also slice thickness is not on here, so write down slice thickness. We're talking about that as well. In a perfect world, we want to have all of these things right here. High signal to noise, which we'll talk about. Good contrast. We want to have high spatial resolution, meaning we want to see things, we want to have high res, right? We want to have high definition. And we want to have short scan times. This is what we strive for. Happy radiologist if we can get this. But in reality, it's a balancing act. If I change a parameter to get better to signal to noise ratio, I'm probably going to affect my scan time, potentially some artifacts, resolution. If I want to get better resolution, same thing. I might affect my signal to noise, scan time. We know if we change our TR, TE, or flip angle, we're going to affect our contrast, right? We're probably going to affect signal to noise, potentially scan time as well. So all of these things balance out. You can't just make a change. Lengthening my TR doesn't just eliminate T1 contrast. It does other things as well. So we want to know what those trade-offs are. So when we make that adjustment, we know what to expect. Following me? So that's kind of what this is about. You got to think about it like if I want to eat, I have to work and give money. So I get food or do something else, right? But you can't just get something for nothing. And that's kind of the idea here. In reality, when we change a parameter to one, to make one of the previous mentioned characteristics, scan time, SNR, resolution, one of those characteristics better, we sacrifice something or affect another characteristic in some way. So that's why we call it a trade-off. And the reason you have this triangle here is because those are the big three. There are other ones, but these are the big three. And what I would do today, maybe to take notes, is kind of make this triangle and start putting different parameters into these categories. And then say what it does if I lower it or higher it, right? So I might be like SNR, put my TE in here. What happens to SNR when I raise my TE or lower it? I'm gonna start putting these things in families for you and start getting you, because some of it's memorization, right? Hopefully you'll start to understand if you're grasping what happens when we wait longer to collect the echo, that's the long TE. What's happening there? What are the mechanisms behind it? So you can start to visualize, oh, I'm getting more dephasing, so maybe my SNR will go down because there's more dephasing, right? Things like that. So it's not just memory, it's conceptualizing what's going on to help you memorize, right? Or help you understand what's happening. So we've talked a lot about signal before, but we've never really talked about signal to noise. Well, we'll abbreviate it SNR. It's a ratio, signal divided by noise. The signal amplitude divided by the amplitude of noise. Amplitude is just how much we have, right? Amplitude in terms of sound is volume, right? So when I'm talking to you, there's waves hitting your ears, right? Compression waves, and they're at a particular amplitude. When I speak up like this, right, the frequency didn't change, but the amplitude did. Much higher amplitude, right? In MR, the amplitude is determined by the amount of transverse magnetization. That's the amount of voltage induced in the coil, right? So signal is the amount of voltage being induced in the coil at the echo time, the center of the echo, which is the TE, right? We've already talked about this. We just haven't talked about what noise is yet. Noise represents frequencies of RF energy that exist randomly in time and space. All of this stuff gets sampled as well as the signal, and everybody's experienced RF noise before. I'll show you in just a minute. But because it is a ratio, this property, due to the math, exists. Anything that raises the signal will raise the SNR. Also, anything that lowers the noise will raise the SNR. So you can think about it mathematically, or you can think about it like this. If all of you were talking, I'm going to have to speak louder for you to hear me, right? But I can speak quiet like this because none of you are talking. You can hear me well because the noise is low, right? So if the noise is high, the signal to noise will be low. But if the noise is low, the signal to noise will be higher. Also, if the signal's high, obviously the SNR is going to be high. If the signal's lower, the SNR will be lower, right? think about it in terms of math. Let's say I have 2 signal and 4 noise, right? S divided by noise, signal divided by noise, that's the ratio. This basically is 1/2, right? 2 divided by 4 is 1/2. Obviously, if I raise this, it's gonna be higher, right? So if I raise my signal to 4, I didn't touch my noise, 1 is greater than 1/2, right? I made this number larger by raising the signal, but I could also make this number larger by lowering the noise, right? If I kept my signal the same, but lowered the noise to 2, this number is also bigger now, right? This is still 1 as opposed to 1/2. So I show you this because some people like the math, it resonates with them. Other people hate the math, but. You guys understand what signal and noise is now? Noise, I'll show you exactly what noise is, but let's talk about what it makes images look like. We have an axial of a brain right here. This is a low SNR image versus a high SNR image. And I don't want everybody to get confused and say, oh, this is a bad image. Depending on what we're trying to achieve, it might be acceptable. We're not always trying for the highest SNR. We want high SNR, we want images to look better, but it's relative to what we're trying to do, right? And it's a trade-off. But I need you to understand, if I'm looking at this, it has lower SNR, it looks grainy, right? You see that grain in there? We can also say it looks noisy. This doesn't look like that, right? Hopefully you can tell the difference. And the reason I'm giving you this verbiage is because I might say, this image looks grainy, what do I need to do? The image looks noisy, what do we want to do to fix that? We want to do something to improve the SNR, right? So if an image is looking like this, you as a technologist know, if I want that to go away, I have to do something to get better SNR. I need to raise my signal or lower my noise somehow, right? Here's another example, high SNR, low SNR. You can see it's grainy. We call that grainy, we call it poor SNR, we call it noisy. So what is noise? Anybody watched an old school TV with an antenna and you get that static, they call it, right? You're not receiving enough signal, but you're receiving something. It's noise. If there was nothing being picked up by the antenna, none of this would happen. It would just be blank, right? This is actual RF noise being picked up by the antenna. And that's what that sound is too, right? I think this lasts for 4 hours. We're gonna watch it. But it's essentially, it's information that doesn't mean anything. It's not carrying any, or it's RF that's not carrying any coded information, right? But this noise exists. I'm sure if you haven't seen this before, some of you have driven away listening to an AM or FM radio and on a long road trip, and all of a sudden you start losing signal and you just hear, right? You start hearing that noise. That's what that is. It's just random noise, and it exists at every frequency in the bandwidth. Closer, guys.
Check out Brian.
Yes.
Are you adjusting these parameters while you're scanning or after the sequence?
If you're gonna adjust parameters, it's before you start the sequence. Yeah, it's before you start the sequence.
So how do you know you have noise?
Well, you won't until you see the images.
So basically,
So remember, I said at the beginning, we're not adjusting these typically as we go, right? These parameters are set. We're not putting them in right before we start the scan. They're saved there. We make adjustments if we need to.
after the sequence, alright?
Yeah,
Because then.
or if you're thinking, like, say your coil's broken, you're using a different coil, you're like, okay, this coil's not gonna produce as much signal, so I need to make adjustments beforehand and hope that I get better quality images. Or if the radiologist says, I really don't like the T2 contrast on this, make it better, you need to know what to do that beforehand.
The patient, but the patient will still be in the floor, right, at that moment?
Yeah, but I mean, you might
You should know at that point, if your radiologist, before you can scan it, the radiologist comes in, I don't like the T2 contrast on the ones I've seen previously, make it better. You should know what to do at that point. What causes noise? It's generated by the presence of the patient in the magnet. We all have electrical energy in us, right? We have magnets in us, we know. We generate noise. Noise comes down from outer space, right? All of our devices create noise. So generated by the presence of the patient in the magnet and the background electrical noise of the system. There's not much other noise coming from space because why? In the magnet anyway, in the magnet room, we shield it, right? Faraday cage, we're keeping all that noise out, but there's still noise within the patient and the electrical system in the magnet. So what can determine noise? Well, the build of the patient, the area under examination, inherent noise of your MR system, and it occurs randomly at every frequency. That's important to know. It's just random, but it is at every frequency. So any frequency we sample is going to have noise, or any range of frequencies we sample. Signal, on the other hand, is cumulative and predictable. It's not random, it's predictable. We can predict it. It's based off of magnetic field strength, right? Proton density of the area, coil type and position, TRTE and flip angle affected. Something called NEX, or number of signal averages. We'll talk about all of these. Receive bandwidth actually controls noise, not signal. But this does help with SNR. Receive bandwidth controls the amount of noise we sample, but not signal. Voxel volume 2 controls the amount of signal that we have. So we'll go through each one of these and talk about why. This one should be obvious, right? Magnetic field strength. The more protons we have that align with the main magnetic field versus against is going to give us a larger NMV, right? That NMV is our longitudinal magnetization in equilibrium to flip into the transverse plane. So at a 3 Tesla, I'm going to have a lot more NMV than I will at a 1 Tesla, right? I have much more potential to flip all of that into the transverse plane. Therefore, I have more SNR. So I have more, what kind of protons? Low energy, spin up, parallel protons, right? In a higher field magnet. So that should make sense. And this is kind of like the currency. Our NMV, the size of the NMV is the currency we use. We trade that in for everything else, right? This is going to be a big factor to determine how much SNR my image is going to have. There. Higher field strength, larger NMV, therefore more signal to start off with. Lower field strength systems need to do other things to increase SNR. There's going to be some other stuff that we talk about that's going to help increase that signal. But if we start off with a large NMV, we have a lot more money to play with, essentially. A lot more currency to trade in. Proton density should be relatively obvious as well. Right? The more proton dense a given tissue is, the higher the NMV of that tissue, regardless of the field strength, right? The more protons, the higher the SNR, the higher the signal. Areas that have high proton density, like fat, the bladder, renal pelvis, all of those areas have high proton density. They're going to produce bright signal if we set the parameters properly, right? Some areas in your body have low proton density. Cortical bone, we don't see cortical bone very well in MRI because it has low proton density. Also dephases very fast. Also the lungs. MRI doesn't image the lung. It's not the gold standard for imaging the lungs. CT is at this point, right? And that's because of this. Someday we'll be able to image the lungs. There'll be advancements in MRI to allow us to do that. They already have some techniques where you inhale a gas in MRI, and it's a gas that actually is resonant. I mean, it produces signal. It's not hydrogen. Obviously, you don't want to inhale hydrogen gas, but it's something else that's not toxic. That is NMR reactive. You set your machine to cause that to resonate and to get the signal back, and they can produce decent images of the lungs. Typically looking at airflow, though, when they're doing that, it's not common, but it can be done. Yeah.
So, we talk about magnetic field strength. How does that affect signal to noise? Higher field strength, more signal, right? More proton density, more signal. All these should be obvious so far. Type of coil. Larger coils receive more noise in proportion to signal. Larger coils cover more area, but they're just not as efficient. They collect more noise, right? So it's better to have a bunch of smaller coils that are all phased together or arrayed. Smaller coils are going to have higher SNR than larger coils because they're not going to be picking up as much noise. Also, proximity. Surface coils that are closer to the area being examined are going to produce higher SNR. So instead of having a big coil wrapped around, if I have a surface coil that's right near, like, say, my spine. Remember, the coil has a signal profile, right? It fades off as you get further away from center and further away from the coil. So if the coil is closer to the area of interest, it's going to produce higher SNR. Also, quadrature coils, we talked about these briefly, and phase array coils. They all produce better SNR because it's multiple coils, smaller elements that are all gathering signal that get added together. So a single element on its own is not going to be that much, but if we array them together, then we can get more signal added up, cumulative signal, essentially. So coil affects it. More expensive coils are going to be phased array or quadrature, right? And they're going to be smaller elements that are arrayed together. That's why I was saying earlier, if you have to use a larger coil, let's say you have a patient that has a giant knee for whatever reason, because of their body habitus, maybe they had some injury, and it does not fit in your knee coil. You're going to have to wrap your abdomen or body coil around it, which is going to be larger elements. So already I'm going in with less signal. So at that point, you got to make some changes to get yourself back some better SNR. So it's just things to keep in mind, or that's just an example of how coils may affect our SNR. Coil position, we already talked about this, but here's some examples. It's really important that you position your coil correctly. Remember, the coil element has to run parallel to B0, right? This is running parallel to B0. This is also running parallel to B0, right? It's running in the same direction. If we loop our finger around the coil, it's moving with B0. It's going in the direction of B0, right? Same with this. This isn't though, right? There's no transverse magnetization cutting through this coil. It is looped in the transverse plane. This one is 45 degree. It's kind of in the transverse plane, kind of in the longitudinal plane, but you can see the difference in the SNR, right? The coil is positioned properly, we get good SNR. It's a little angled. It's not completely running with B0 anymore. We can see we start to lose SNR. It starts to look more grainy, right? And then this one, we don't really even see anything. It's not producing basically any signal at all, right? So coil position, we already talked about this, but if you're ever scanning and you're using a coil and it's in an awkward position because the patient is in an awkward position and you're not getting any SNR, make sure you check your coil. Make sure that it is running in the right direction. Those are all the easy ones. Now we start getting into the trade-offs. And like I mentioned before, I would have that triangle out of SNR, resolution, scan time, and I would also put contrast on there. And I would put certain artifacts as well, right? So the big three are SNR, scan time, resolution, but also contrast, because we know TR, TE, and flip angle affect contrast, and then certain artifacts we will talk about as well. But how is SNR affected by TR? If SNR is increased, what happens to if our TR is increased, what happens to our SNR? It increases, right? Why? Because we're allowing for full longitudinal recovery, right? Basically like starting off at equilibrium every time because we're waiting for everything to fully recover back. We do it again, right? So a longer TR will improve your SNR. On the other hand, a shorter TR will decrease your SNR, right? Because we don't have as much longitudinal magnetization recovery to flip into the transverse plane. Following me? But we know that if we want T1 weighting, we need a short TR, right? So we're already affecting our SNR to get better T1 contrast, right? So what's the trade-off right there? Lowering my TR gives me better T1 weighting, but I'm sacrificing what? SNR, right? So you are already sacrificing SNR to get T1 weighting. Following me? So it's not something like, I think a lot of people get confused. It's like, well, why would you want to do that? Because you're getting worse SNR. It's like, no, I'm sacrificing it for something else, right? It's a trade-off. Doesn't mean our SNR is going to look bad. Just means that we have to do other things to get more signal back or lower more noise so that we can get a good looking image. Here's some examples. This is a T1 weighted image, so we know the TE is short as well. You can see it goes A, B, C, D. A is 700 milliseconds, right? We're at the top edge of what our TR needs to be for a T1 weighted image. 500, 300, and 140, right? If we lower our TR too much, it's a lot of contrast here, right? But too much, we don't see contrast between the different tissues in the brain. We see bright fat and nothing else, right? Very high contrast, but no signal. We can't really see what's going on in there. On the other hand, we weighted a longer TR. We could see this much better. But check out the 500. Which one has a little bit better contrast? Look at the white gray matter contrast in B. Right? There's a little bit better contrast here. The white gray matter, you can see it a little bit better. Even though this one is slightly more grainy, it has a little bit better contrast than this one does, right? So you can see I'm sacrificing SNR for T1 contrast, right? But I can't go too far, right? This is starting to look bad. And then can't even see anything at all, right? There as well. 100 milliseconds, 350, 750, right? You can see the difference. Not much signal, right? Got my signal back. I have some pretty decent contrast there too. Go a little bit higher, still have contrast, not as much as here, but you can definitely see this one's not grainy at all. There's no grain in this one where you see a little bit in here. Right. So what's my trade-off for my TR? Higher TR does what? It raises our SNR, but we're sacrificing T1 information, right? We're also sacrificing scan time. Put that in there. Scan time, we'll get to that slide, but scan time is TR times next times phase matrix. So TR, raising your TR is going to raise your scan time. Just write that down now. We'll get back. There'll be a slide on scan time. We're gonna have to calculate scan times, so we'll get there. But I just want to, as we're going through it, start telling you what these trade-offs are. We'll discuss them all separately. Any questions or we're good to go? That was TR. Flip angle. TR and flip angle work together. You know this, right? If we have a short TR, we have to change that flip angle to either allow full recovery and eliminate T1 contrast or to get T1 contrast, right? However, with a long TR, a 90-degree flip angle will produce the best signal for us, right? Long TR means full longitudinal recovery. Therefore, to get the most transverse magnetization, where do I need to flip it to? 90 degrees, right? That's where I'm going to get my most SNR right there. The long TR allows for more longitudinal recovery, which can then be reflipped completely into the transverse plane. Making sense? So with a long TR, what flip angle is going to give you the most signal? 90, right? Because if I only flip it a little bit, let's say the 30-degree flip angle, look at my transverse magnetization. It's not as much as if I flipped it all the way to 90, right? So if I have a long TR and I only flip it 30 degrees, I'm not going to get as much SNR. As you can see here. Long TR, we don't know what it is, but we can see a flip angle of 10 versus the flip angle of 90, right? Which one looks less grainy? The 90, right? With a long TR, the 90-degree flip angle produces the highest signal. However, with shorter TRs, 90 might not be your best bet. With shorter TRs, we might want to flip it just not as much. This is called the Ernst angle. With a short TR, only partial longitudinal recovery happens, right? So we can see a short TR, we're watching our longitudinal recovery only having a little bit, right? So if we flip that 90 again, we don't have much to flip 90 degrees, right? We flipped it 90 to begin with. We don't have any longitudinal magnetization. It recovers a little bit. We don't flip much into the transverse plane. If on that same short TR, we only flipped it 30, it's going to recover back, flip it again. We're going to get more transverse magnetization on a short TR with a lower flip angle. And it's dependent upon that tissue's T1 recovery time. With a very short TR, fat still might recover back fast enough to where 90 is going to be the best SNR, right? But for tissues that take a long time, 90 might not be the best flip angle to produce the best SNR on a short TR. The Ernst angle is the highest SNR produced by any given tissue per given TR. So if I give you a TR and I want to know what the highest signal water will create at a given TR, I can tell you that angle, and that angle is the Ernst angle. It's not something you need to know as MRI techs, like you're not going to have to memorize Ernst angles. You just got to kind of understand what it is. So let me give you an example. Let's go back to here. This is a short TR, right? This is a very short TR. I could have maybe changed my flip angle here to get the tissues in here to look brighter, right? If I wanted water to look bright, I probably could have changed my flip angle to like 20 as opposed to 90, and then it would have looked bright. That would have been the Ernst angle at this given TR. To get water to look the brightest that it needs to at 100 milliseconds, there's a particular angle. There's a particular flip angle that we can prescribe, and that is called the Ernst angle. You can see fat is still really bright, right? So the Ernst angle for fat at this low TR at 100 milliseconds might be 90 still. But for every other tissue, it's going to be something lower, right? If you're not fully understanding that, just know that with shorter TRs, 90 is not always the best. 90-degree flip angle is not always going to produce the best SNR, particularly with tissues that have a long longitudinal recovery time. Following me? With a long TR, what is the flip angle you want for the best SNR? 90, right? For shorter TRs, it can change. It's going to probably be lower flip angles, dependent upon the tissue we're looking at. You good with TR and flip angle? What's the trade-off though? Like say I have a short TR and I want to go with a lower flip angle to get better SNR. What's the trade-off? What kind of contrast? T1, right? So if I want to get T1 contrast and I lower my flip angle to get better SNR, I'm sacrificing that contrast. I can't do it. Gotta know the trade-offs. Okay, I'm just giving you complex examples here. We'll keep going over them. Echo time, TE, we know this is, it's the center, it's the peak of the echo, where the highest signal is induced in the coil when we are sampling. TE controls the amount of transverse magnetization is happening, right? Before we sample that echo. A long TE allows for a lot of dephasing. So what do you think happens to the signal? Goes down, right? Longer TEs produce lower SNR. Shorter TEs produce higher SNR, right? If this is our timeline right here, we can see more dephasing happens, lower transverse magnetization. We sample right here, plenty of SNR, lots of transverse magnetization, given that it was a long TR to begin with, right? Here we go. Once again, showing TEs of, actually this is showing TEs as opposed to TRs. It's a short TR, we know that. Why? Because it looks T1 weighted. We're suppressing water, right? So this is a T1 weighted image. We can see the different TEs. We describe now 11, 20, 40, and 80. You can see how the signal goes away as we are increasing our TE. This is why there is no short TR, long TE sequence, right? Produces nothing here. All the signal goes away. What does a short TR do to our SNR? Decreases it, right? What does a long TE do to SNR? Double decrease, right? We just see nothing here. But look at what happens to the well, this would be the best contrast. We're not worried. We're mixing T2 and T1 information here, which just produces no signal. But we want in a T1 weighted image with that short TR anyway, that's already lowering our signal. We want to have the TE as low as possible to give us the best signal possible with that short TR and short TE. Let's look at T2 weighted, right? You can see high SNR. Still high SNR, but what's getting better here? T2 contrast is getting better, right? And you can see here, a lot of contrast, but it's starting to look what? Grainy, right? We're losing SNR. This is a little bit outside of our T2 ranges. Depending on what body part we're looking at, this actually might be a good TE for T2, depending on what we're looking at. But in the brain, it's starting to get a little grainy, right? Look at over here. Smooth, lots of signal. I see no grain. I see no noise. Kind of weak contrast though, right? Everything kind of looks similar. I don't have a lot of differences in tissues. Starting to see it here, right? We increased our TE to give us better what? T2 contrast, but what are we sacrificing? Signal, right? Another trade-off. How are we doing? Okay. If I want better T2 weighting, what do I need to do? We need to increase the TE, right? What's my trade-off? Yeah, I'm trading a little signal in for better T2 weighting, right? Does it affect my scan time? It does not. TE has no impact on scan time. All right. Next, NSA, number of signal averages. Unfortunately, the vendors don't call this the same thing. GE, as you can tell by the, we go back. GE calls it NEX. Siemens calls it averages. Philips and Toshiba, I think, call it NSA or number of signal averages. So depending on which vendor you're using, it's going to be called something different. But it means the same thing. We'll talk about what that is. Right here, NEX. Number of excitations. This parameter controls the number of echoes stored per line of K-space. What was K-space again? We talked about it a few weeks ago. It's where the echoes go. It's raw data that is turned into an image. So it's essentially just, it's sampled data from the echoes
from several echoes that gets turned into the image.
The number of echoes collected with the same phase encoding amplitude, that's not gonna make much sense to you now, but increasing next increases our SNR. So let me show you what K-space looks like here. This is K-space. These represent echoes, several echoes being collected over time. You collect one echo per TR in a spin echo sequence, and we have to collect several of them. We have to fill up all of K-space with at least one echo to generate an image with the resolution that we desire. A next of one means that we fill each row one, or each line of K-space, each row one time. We put one echo in there. So we sample it once, we give it a certain amount of phase encoding, which we'll talk about in physics too, and we put it in that line of K-space and we call it good. Then we go to the next one, the next one, the next one, until we fill all of them. The amount of echoes we need to collect is determined by the phase matrix. We'll talk about that later. But it does impact our resolution. So the amount of lines in K-space that we collect affects our image resolution. But the amount of times we fill each one of those lines affects our SNR. And next controls how many times we fill each one of these lines. A next of one means we fill each line with one echo. A next of two means we go back and fill each line with a second echo. Next of three echoes per line, and so on and so forth. And they get averaged together because each echo contains noise and signal, and it gives us overall better SNR. Right? So think about it. If I pull in a little bit of light, got a little bit of light in the box, like, oh, I can barely see anything, pull in some more light, you're just adding it over time, right? Same thing here, we're pulling in some signal, we're collecting it, and then we're doing it again to get more overall SNR. More data sampled means more signal sampled, but also more noise sampled. But we're sampling more signal than we are noise, so our overall SNR increases as our next increases. We collect one echo per TR in a spin echo pulse sequence. Since every echo contains both signal and noise, we do not increase our signal linearly when we increase our next. Right? So if I have, say my SNR is 100, putting a number out there, it's 100%, whatever that means. If I take my next and I go from 1 to 2, I don't have 200 SNR now, right? That would be a linear relationship, right? I'm not doubling my SNR by doubling my next. The relationship is that we are increasing it by the square root of the factor of increase of next. So if I double my next, I take the square root of 2, and that is what my new SNR is. And you can see that here. From 1 to 2 to 3 to 4, right? If you quadruple your next, what is the square root of 4? Right? The square root is what times itself equals that number. So 2 times 2 equals 4, right? So by quadrupling my next, I get double the signal. And you can see here, we started off with 1, now we have 2, right? If I wanted 3 times the signal, what do I need to do? Go to 9, right? What's the square root of 9? 3. 3 times 3 equals 9. Right? So it's the square root. So let me state it this way. The factor by which SNR increases is by the square root of the factor of the increase of next. I know that sounds scary, but you just have to know what am I multiplying my original next by to get my new next? And if I take the square root of that, that's going to be my SNR increase. So, say my original next was 2. The next in the machine, in the protocol said 2. And I'm like, I don't like the image quality, I'm going to double that. I'm going to double it and make it 4. What times 2 equals 4? 2, right? So the factor of increase equals 2, right? This one always confuses people because 2 plus 2 also equals 4. But it's not what we added, it's what we multiplied by, right? The square root of this number equals about 1.41. That means that my signal increased by 41%. So if my original SNR was 100, and I increase my next, I just multiply this number by 100 to give me 141, right? So my signal went up from 100 to 141 by doubling my next. One to two, it's the same thing, right? My original next was 1. And I went to 2. What is the factor of increase? That's what people get. It's not what you add it by, it's what you multiply it by, right? So 1 times 2 equals 2. So I get 41% more signal from going from 1 to 2. And the reason that it's not a direct increase or a linear increase is because we're sampling noise too. Right? So if I asked you this question, say my next was 1 and I increased it to 3. My original SNR equals 100. What's my new SNR? How do we figure this out? First, though, we want to figure out our factor of increase, right? You guys are right, but we want to make sure that we know that factor of increase first. What times 1 equals 3? 3, right? So my factor of increase equals 3. What do I do with this number? Take the square root of 3. What does that equal? I don't have a calculator, but it's like, I think it's like 1.73 approximately. You all should have square roots on your calculators. You can use these for the test. Am I right? Yeah. And you can see here, 1 to here to 3, right? That looks about 73%. So my new SNR is 100 times 1.73 is 73% more signal, right? By tripling the next. Here's the trade-off though. What happens if I increase my next besides getting better SNR? It is, because my scan time equation is TR times next times something called the phase matrix. So in this case, I've got 73% more SNR, but what have I done to my scan time? Tripled it, right? 3 times the scan time for 73% more signal. Is that efficient? Maybe, maybe not. So write that down in your little triangle. Next, increasing it increases our SNR by the factor of the square root of increase. But it also directly increases my scan time linearly, right? Let's say my original scan time was 2 minutes. What's my new scan time? 6, right? Multiplying it by 3. I got 73% more signal, but it's taking me 3 times as long. People get confused in this all the time. You're gonna be asked questions. How much longer is my scan time if I double my next or triple my next? People will say the square root of the, no, that's not it. It would be triple your scan time. If I asked you how much more SNR you're getting, yes, you're right. It's the square root of the factor of the increase. Want to do more of these?
Yes.
Let's continue. All right, my first next was 2. With that next, my original SNR was 100 and my original scan time was 1 minute and 30 seconds. What happens to SNR and scan time if I increase my next from 2 to 8? So what's the factor of increase here? What times 2 equals 8? 4, right? It's not 6. We're not adding, we're multiplying, right? So my factor of increase equals 4. So I can figure out right now how much more scan time I have. Right? Take that 4 and multiply it by what? Right? So 1.5 times 4 is 1.5 times 4. I think you're right. I think it is 6. Right? 1 minute and 30 seconds. That's 1.5 minutes times 4. 6, right? Yeah. Now, so it's not, we're not doing 1.3 times 4, we're doing 1.5 because that's 30 seconds is half of a minute, right? So the scan time now equals 6 minutes. So we went from 1 minute, 30 seconds to 6 minutes. How much more SNR do we have? How do I figure that out? What do I have to do to the square root of 4 equals 2, right? So my new SNR is 200. So to double my SNR, I have to have 4 times the scan time, right? If I'm using next only. Factor of increase. You want to figure out new scan time, you take your factor of increase and you multiply it by your scan time. If you want to figure out your new next, you take your factor of increase, square root it first, and then multiply that by your SNR. Where there's not much more math. That's the hardest, at least in this. So here we go. If next is increased by a factor of 2, then the signal is square root of 2, 1.41 more than it was before. Here we go. We have a field of view. Field of view, TR, TE are both the same in both of these, right? I have a next of 1 here and a next of 4 there. You can see the difference, right? Which one looks grainy? 1. We didn't change anything else but our next, right? So we have a new picture that looks a lot less grainy. What happened to my scan time though in this one versus this? How much longer? Quadruple, right? 4 times longer. We don't know what the scan time is, but whatever it was here, it's 4 times more there, right? How much more SNR do we have here than we did here? Well, I'm not showing you an original SNR, but whatever it was, what is the new SNR? Twice, right? Square root of the factor of increase, which is 4. Square root of 4 is 2. 2 times the signal, 4 times the scan time. Understanding next, kind of? So remember, K-space. K-space is where the raw data is collected. Raw data is our echoes. We sample echoes, we put them in K-space. How many rows of K-space do we need to collect? That's determined by our phase matrix, which we'll talk about, which has it's a resolution parameter. How many times do we fill each line of K-space? That's determined by what? Next, right? So if I have K-space and it has 300 lines, K-space, there are 300 lines. I have to collect 300 echoes and fill each one of those lines once. That's a next of 1. If I have a next of 2, I gotta go back and collect each one of those again. So I'm collecting 600 echoes, right? which is why it's taking me, and if I can collect 1 echo per TR, I have to keep going through all these TRs, right? That's why it's costing me more time. Feeling good with next? If I gave you a change in next, could you tell me what the trade-offs were? If I increase my next by 3 times, what are my trade-offs? More scan time, how much more? Triple, right? How much more SNR? The square root of 3 more, right? Whatever that is, 1.73, I think. Receive bandwidth. People get scared by bandwidth. You hear the word all the time. How much bandwidth do you have? What is bandwidth? I want to make it simple for you. It is a range of frequencies. That's all it is. A frequency, remember, an MRI, it's how many times that proton is processing past the coil, right, in a given second. So it's in megahertz, right? A range of frequencies would be how many, it would essentially be that frequency and then many others, right? So if I had a frequency from say 1 hertz up to 10, I have a bandwidth of 10 hertz, right? So I had something processing at 1 hertz, something else processing at 2 hertz, 3 hertz, 4 hertz, all the way up to 10 hertz. There would be a bandwidth of 10 hertz, right? It's just a range of frequencies. Obviously, we have in between that, we can be in between 1 and 2. There's infinite amounts of frequencies in there, depending on how we want to cut it, right? But that range of frequencies is 10 hertz. Got 1 hertz over here, 10 over here, and all the frequencies in between. That's what a bandwidth is. Does that make sense? When we talk about bandwidth in like internet terms or Wi-Fi, it's literally the range of frequencies that are sending that information to your computer, because everything is transmitted via frequencies. So it's just RF frequencies that are carrying data in a certain way. It gets a lot more complicated, but we'll talk about it in frequency modulation radio. That's what FM stands for. AM is amplitude modulation. But it's these range of frequencies in the RF bandwidth that carry information. Bandwidth is a range of frequencies. When we tune into an FM radio station, we are actually tuning into several frequencies and ignoring the rest. An FM radio station has a bandwidth or a range of frequencies of 200 kilohertz. So we think, we turn into 93.1 or 103.7, whatever it is, right? We think that we're tuning into just one set of frequencies. No, we're tuning into a range of frequencies that's 200 kilohertz, 100 minus that station and 100 plus. That's why you've never seen a radio station with an even number, right? They're always odd. So this is 103.7 megahertz, right? So here, notice that all the FM radio stations end in an odd number, 88.1 all the way up to 97.9. The entire FM bandwidth is from 88 to 108 megahertz. So we can say that the FM bandwidth is 108 minus 88, whatever that number is, 20. Yeah, 20 megahertz is the FM bandwidth. But each station in there has a bandwidth of 200 kilohertz. When I tune into 88.1, I'm actually receiving RF from 88 megahertz all the way up to 88.2. That is 200 kilohertz. So the data that's coming in is modulated through all of those 200 kilohertz of frequencies, that bandwidth. The center frequency would be 88.1. That's in the center, right? And we have other frequencies on each side that are carrying information too. So how does this relate in MRI? Why would we have a range of frequencies? We know we have the precessional frequency of hydrogen when we excite, right? So why would, there's not a range, that's just one frequency. When we're talking about receive bandwidth, we're talking about the signal that is coming back, or the range of frequencies that we're listening to or sampling during echo collection. We're not just collecting one frequency, as common sense would tell us. We're collecting a range of frequencies, and we are actually creating this range of frequencies by turning a gradient on. That range of frequencies during echo collection is called our receive bandwidth. And it is another parameter that we can change as an operator. There it is. 125. And GE, this means plus or minus 125 kilohertz. That means the total bandwidth here is 250 kilohertz across the field of view that we're looking at, across the image. You can change this, right? I could say, no, I only want 60 kilohertz, or I want 50, or I want 300. That's something that you can change as an operator. But what is that doing to the system? Y'all hate me at this point? So look, this is a range of perceptual frequencies that are being sampled during the echo collection. We need to create a range of frequencies so that we can see the experience differences in where the protons are across the field of view. It's how we spatially localize. If everything came back in one frequency, we didn't know where the hell they came from, right? Be like, we know it's in that slice, but is it your ear? Is it your nose? Is it the other ear? We only know that if we create a range of frequencies or a bandwidth across the field of view. This is done by putting on a gradient, called our frequency encoding gradient during the echo collection, right? So we see right here, this is 42.6, right? That is our center frequency at a 1 Tesla magnet. If we turn a gradient on, the center of the magnet will still have protons processing at 42.6. But some of them will process higher on one side and some of them will process lower on the other side. Or we can see here, it's we're not showing the other side. We keep going down this way. This is our center frequency. And if our gradient's on, as we move up the gradient, we're going to have higher frequencies, right? And we are sampling that during echo collection. This is what we are doing. So the receive bandwidth is created by applying a gradient, right? During echo collection. If we didn't apply a gradient, our the frequency we would be sampling would be 42.57 in a 1 Tesla magnet. Is that a bandwidth? It's just one frequency. Remember, a bandwidth is a range of frequencies. So when we prescribe a bandwidth, it is telling the machine to turn the gradient on to a particular amplitude. The higher the bandwidth, the steeper the gradient, right? The lower the bandwidth, the shallower the gradient. And if we didn't turn a gradient on at all, there would be no bandwidth, right? It would just be one frequency.
You said one more time, turn on the gradient to.
Turn on the gradient to create a range of frequencies across the field of view, across whatever we just excited. A larger bandwidth or a higher bandwidth is going to be created by a steeper gradient, creating a larger range of frequencies across the distance. Lower bandwidth is going to cause that gradient to be shallower. Or better said, the shallower gradient is going to cause a lower bandwidth of frequencies across the field of view. But we determine that, right? You're the operator. You can pick it. 125 kilohertz bandwidth. It's making the gradient do this to create a range of frequencies. Put on a 200 kilohertz bandwidth, that gradient is going to be steeper, right? We're passing more current through the coils to get that higher bandwidth. So now that you kind of understand what a receive bandwidth is, right? Why we're doing it will come in the future, but how does it affect our SNR? That's what we want to know. Low bandwidth results in less noise because we're sampling less frequencies. And remember from the beginning, noise is at every frequency randomly, right? So if I'm sampling less frequencies, I'm sampling less noise. Following me? If we're only sampling a small range of frequencies, then we're only sampling a small range of noise at those frequencies. Raising the bandwidth, causing the gradient to go to a higher amplitude, causing a wider range of frequencies across the field of view, it's going to cause us to sample more frequencies. All of those frequencies have more noise. So if I sample more noise, what happens to my SNR? Goes down, right? So a higher bandwidth decreases SNR, lower bandwidth increases SNR. It doesn't change your signal, It just changes the amount of noise being sampled, right? Our signal is going to be the same. Our signal comes from the tissue, whatever's going on in the tissue, and our NR, TE, and these other parameters. The bandwidth affects it, affects the SNR by affecting the amount of noise that we are sampling. For those of you who like math and science and diagrams, here is a wide bandwidth. A wide bandwidth, high amplitude gradient, creating a large range of frequencies, right? The signal, even though the amplitude of the signal here looks like it's lower, the total signal is cumulative. So the area under this curve equals the area under this curve. This is a lower range of frequencies that we're sampling. We're just squeezing all the signal into less frequencies, but it's still the same amount of signal. Wide bandwidth versus narrow bandwidth, right? High bandwidth versus a low bandwidth. So the signal doesn't change. So if we were to take the area under this curve right here, it would equal the area under this curve. It's just spreading, having a wider bandwidth is just spreading the signal out over multiple frequencies. Yes.
Do we use bandwidth for spin echoes?
Yes, you use bandwidth on every type of, good question, because you're like, where's the gradients coming in? Gradients are always there. The spin echo pulse sequence diagram I showed you is oversimplified. There's gradients going off for spatial localization the entire time. And we know now that they're here, so it would look more like this. Since you asked the question, we have excitation, refocusing, signal collecting. At the same time, we're turning on a gradient while that echo is being collected. That gradient being turned on gives us our bandwidth. So wide bandwidth signal is the same as it is with the narrow bandwidth. We're just spreading the signal out over multiple frequencies. But look at the amount of noise we're sampling, right? With this wide bandwidth, a lot more noise down here since it is random at every frequency than it is here, right? So with that narrower bandwidth, the signal doesn't change, but I'm sampling less noise than I am with a wide bandwidth. So overall, my SNR is going to be less with the wide bandwidth than it is with the narrow bandwidth. But there are going to be trade-offs. And I'm just going to have you memorize this for now. We will talk about why this is over and over again, but I just need you to memorize this is the answer. This is what's happening now. A lower bandwidth increases something called chemical shift, which is an artifact. Remember I said some artifacts can be exacerbated if we change certain parameters. So lower bandwidth is going to give me this artifact. You see it a lot wherever you have fat next to tissue that has a lot of water in it. At the beginning of this lecture, I explained that fat processes at a lower frequency than water, right? So if we are applying a gradient, giving us a range of frequencies, fat is going to be mapped slightly over from where it actually exists. And if we have lower, if I have to move over further to find the next frequency, which I'd have to do with a low bandwidth, I'm going to have fat shifted over further. So you notice this little dark line right here on the kidney, and then it's bright on this side, artificially bright here, and then the same thing here, dark on this side, artificially bright right here. That is an artifact. That doesn't really exist in the body. That is called chemical shift. Low bandwidth makes this artifact worse. I'm not expecting you to visualize why yet, but just know this. A high bandwidth is going to make this artifact better. We're going to make it to where we probably can't even see it with a high bandwidth, because we're putting multiple frequencies or a lot more frequencies in a smaller area by increasing the bandwidth, which is making fat and water come closer together. So lower bandwidth, it increases our chemical shift artifact, makes it worse. It also increases our sampling time, which increases our minimum TE available. So just memorize this for now, but for those of you who want the answer. Sampling time, we don't just sample an echo in an instant. We have to take time to sample the data. It takes time to collect an echo. That time it takes is called our sampling rate. How long does it take for us to sample the data we need in an echo? So it's not like if I have a TE of 10, I'm not just sampling data at 10 milliseconds. Sampling a little bit before and a little bit after to collect all the data I need. The center of that echo is the TE, but I'm collecting data a little bit before and a little bit after that 10 milliseconds. With a lower bandwidth, it takes me longer to sample that echo. Sampling time increases. And this is, we'll talk about why in future lectures. Don't worry about it now, but it's something to do with Nyquist theorem. The higher bandwidths, I can sample things much quicker than with lower bandwidths. So if I have to listen to this echo for longer with a lower bandwidth, it's going to increase my minimum TE available. This was my minimum TE available. It's going to move over. It's going to be longer with a lower bandwidth. Honestly, right now, just memorize this. I don't expect you to understand the reasons behind it yet. If you really want to know, I can keep explaining it, but just hit me up outside of this lecture because I don't want to lose everybody. Just know, well, here, let me ask you this. What happens to our SNR if we decrease bandwidth? Increases our SNR, right? Need to know that. But what is the trade-off? Yeah, the chemical shift artifact gets worse. What else? Sampling time goes up, which causes a increase in your minimum TE available. So if I want, let's say I'm prescribing a sequence and I want the shortest TE possible. And the machine's like, your shortest TE available is 10 milliseconds. Sorry. Based on a variety of other things. What can I do to get that TE down? Increase the bandwidth, which will increase the gradient, right? If I increase that bandwidth, make it a higher number, my minimum TE available is going to go down. Allows me to sample data faster and push that minimum TE, squeeze it closer to the excitation pulse. Right? But what's the trade-off for that? What's the trade-off to raising the bandwidth? Nothing to do with scan time.
I'm at SNR.
Yeah, there we go. We have lower SNR by increasing the bandwidth, but we have lower minimum TEs available. Our chemical shift artifact gets better, right? So once again, there's the balance right there. You were right with low. You said lower scan time. You meant sampling time. That's what you meant. Lower sampling time, giving us a lower TE. You're gonna have to know all of these trade-offs. What happens if I decrease my bandwidth, or what doesn't happen? So we all agree if we increase the bandwidth, that means that our gradient amplitude during the echo collection goes up, right? Creating a larger range of frequencies. What happens to my SNR? Goes down, right? Why does the SNR go down? The noise goes up, right? Sampling more noise gives us lower SNR. Because that is the denominator of this increasing, right? Guys good with receiver bandwidth? Remember, bandwidth is just a range of frequencies. Collecting a range of frequencies is done during echo collection by putting on a gradient to give us a range of frequencies. Voxel volume. Everyone's heard of a pixel before, right? The smallest unit of a digital image is a pixel. I literally took this, and I mean, now I pasted it on smaller, but when I pulled this onto my computer, I just zoomed in and this is what I got right here, right? Don't see the pixels here, but when you zoom in, you can see them, right? And you can see each one of those pixels is just one color. There's no, each pixel doesn't have multiple colors, there's one color in there, right? It's the smallest element of a picture, of a digital picture. MRI has the same thing. We have pixels in there that are either large or small, right? All digital images are made up of hundreds of thousands of pixels, each of which consists of only one color. In MRI, it's a grayscale. We have the brightest white and the darkest black, and then all the grays in between. That's what we get in MRI. Pixels are in 2 dimensions though, right? There's not a third dimension here. In MRI, they're voxels. Because in MRI, we excite a slice of tissue. We're not just opening the body up and looking at it as a 2D surface. We actually have to excite protons. And to do that, there has to be a volume excited, right? So in MRI, when we're looking at the picture, it looks 2 dimensions, but it came from 3-dimensional data. It came from 3-dimensional, a 3-dimensional excitation. In MRI, the brightness of the pixels represented by the strength of the signal generated from the volume of tissue in that particular unit. So voxel is literally volume plus pixel. You get the word called voxel. But note in MRI, we're looking at 2D images. We don't yet have these 3D images that are floating around us in 3D space, right? Even if it looks like 3-dimensional, it's still 2D. It's still a 2D image, right? Voxel volume, so think about volume as like a box, right? If you look at a box, you have a small box that has a small volume. That's how much space it takes up, right? So if I have like I need to ship a watch to somebody, I'm gonna have a small volume box that I'm gonna ship it with, right? If I need to ship a basketball to somebody, the box is gonna have a larger volume. It's gonna have more space inside it so that I can utilize that room to ship what I need to. In MRI too, these voxels have a volume that can be calculated, right? They're going to be much smaller than the pieces I was talking about, but these volumes can be calculated. And they are calculated by pixel area and slice thickness. Slice thickness is a parameter that we select. If you look at you go back to the sheet that I was showing before, the user interface. You can see right here, we have a slice thickness of 5. Right? That's in millimeters. So a centimeter is about that. There's 10 millimeters in a centimeter. So that slice is about that thick in this case, right? The pixel area is our field of view divided by something called our matrix. And we have 2 different matrices. We have a frequency and phase matrix. Think about a pizza as your field of view. Your matrix is how many pieces you cut that field of view into. Let's not think about a round pizza. Let's think about a Sicilian pizza. They're square, right? And rectangular. How do you cut those pizzas? Into squares, right? That is kind of what we are doing in MRI to determine our voxel volume, or our pixel area. So this is my Sicilian style pizza. I'm not just going to eat the whole thing. I might, but we probably just want to share it with people, right? We're going to cut it. Let's make it a square though. Because in MRI, that frequency field of view is square. We're going to cut it into multiple pieces in different directions, right? In 2 directions. We're going to slice it like this. And we're going to slice it like this. Right? And that is going to give us the size of the pizza pieces, right? Our field of view is how big the entire pizza is. Right? So in this case, it's 24 centimeters. That's a good like sagittal of the head. That's a good size for sagittal. 24 centimeters is probably about that, right? We are cutting it on one side into 256 pieces. I'm always not going to draw that many lines, but 256 pieces on one side. That is going to determine the size of my pizza in this direction, right? The other direction, we're only cutting it into 128 pieces.
which we did here. That's gonna determine the size of my slices in this direction. Right? And then also, remember this pizza is real, so it has some sort of thickness too, right? That is a dimension as well. That thickness of the pizza is gonna determine how thick each one of those slices are, right? It's gonna determine the volume of each slice of pizza. Deep dish pizza, we'll call it deep dish pizza. So in MRI, our voxel volume is determined by our field of view divided by each matrix, right? You multiply each one of those together, and then you multiply it by your slice thickness. That gives you your voxel volume. So here, voxel volume is determined by pixel area. How do we find pixel area? Field of view divided by our matrix. We have two matrices, right? We're cutting this in two different directions, cutting it this way and this way, right? That is our matrix, our frequency and our phase matrix. You multiply those together, that gives you your pixel area, and then you multiply it by your slice thickness to get your voxel volume. The reason voxel volume is important in SNR is because the larger the voxel, the more protons it can hold. If it can hold more protons, what do you think happens to the SNR? It increases, right? The bigger the pizza slice I have, the more stuff's there, right? More stuff to eat. So in voxels and MRI, if I have larger voxels in my image, I'm gonna have better SNR. Just because there's more protons there. Think of the voxels as little boxes of protons. Smaller the box of protons, the less SNR I'm gonna have. The larger the box of protons, the larger the SNR I have. So, if I determine my voxel volume and I have a number there by calculating it, the higher the number I have, the better the SNR. Any parameter that changes voxel volume will change SNR then. What affects our voxel volume? Field of view, matrix, and slice thickness, right? So anything I change in the field of view to give me a smaller voxel will give me less SNR. Anything I change in the matrix to give me a smaller voxel will give me less SNR. Anything I change in my slice thickness to give me a smaller voxel will give me less SNR. And this becomes confusing. It's pretty simple with field of view and slice thickness, but the matrix confuses everybody. But it won't after this. How do I make these pizza slices smaller? What can I do? Cut it into more pieces, right? Which is increasing my matrix, right? If I want these pizza slices smaller, I increase my matrix. Remember, I was cutting it into 128 pieces on this side. Now I'm going to cut it into 256, right? What happened to each one of those slices of pizza? Got smaller, right? What else could I do? Think of magic ray, shrink the whole thing down, right? Lower my field of view. Still going to be cut into that many pieces. I'm not going to draw these lines again. But it's going to make my pieces smaller, right? So shrinking your field of view makes your voxel smaller. Increasing your matrix makes your voxel smaller. I could also slice off some of the thickness. I could cut that in half right there. Say, nope, I only want it this thick now. That is going to lower that pizza slice, right? That voxel volume. So lowering my voxel volume can be done by doing what to the field of view? Decreasing it. Doing what to the slice thickness? Decreasing it. And doing what to the matrix? Increasing it, right? I will go for the absurdly small so that it makes sense. What is my matrix here?
2 by 2, right? It's a 2 by 2 matrix. If I want to get these voxels smaller, I'll keep my matrix the same, but lower my field of view, right? Still 2 by 2. Which one has the smaller voxel? This one, right? Which one has the lower SNR? This one, right? I can fit more protons in here than I can in these little boxes, right? So lowering your field of view, keeping your matrix the same, lowers your voxel volume and lowers your SNR. What if I did this though? Smaller field of view, finer matrix, coarser matrix, larger field of view, finer matrix. Which one has better SNR? This one, right? Because look at the voxel size. It is obviously bigger than this one is, right? So increasing your matrix does what to your SNR? Decreases it, right? Decreasing your field of view, keeping the same matrix does what to your SNR? Decreases it, right? If this was the same, if it was 2 by 2 by 2 by 2, we can see that the pixel or the voxel obviously got smaller, right? And then slice thickness with the same matrix, 2 by 2, if I have one that has a really thick slice versus one that has a really thin slice, which one has the larger box to fit protons in? One on the left, right? So which one has better SNR? This one, right? The one with the thicker slice. Even though the field of view and the matrix are the same, these are bigger boxes to fit more protons in. All right. So let's see where this goes. It all gets projected onto a 2D image, but it's being collected in 3 dimensions, right? Because we have to have a certain volume of something in 3D space to collect. We have to have a certain volume of protons. We can't excite an infinitely thin layer of protons. There has to be something there. So take a look at this. Decreasing the slice thickness results in smaller voxels, right? So you see I have the same field of view, 40 millimeters across. Our matrix is what? 4 by 4, right? So we can, our voxel volume here and our slice thickness is 10 millimeters. So if we look at it, we do the math, we have 10 by 10 by 10, right? 40 divided into 4 on each side is 10. So I have 10 in this direction, 10 in this direction, and 10 thick. Multiply all those together to get me my volume, right? What is that? 1,000 millimeters cubed, right? That is my voxel volume in this case. What happens if we halve our slice thickness to 5? Right? Our pixel area is still the same, right? It's 100, 10 by 10, but now we multiply it by 5. We can already see this is a much smaller box than this, right? Our voxel volume is 500 millimeters cubed. It's half of what it was before. What do you think happened to the SNR? By how much? Half. So it is a linear relationship here, right? Voxel size and SNR is a linear relationship. If I half my voxel volume by having my slice thickness, I have half the SNR. And vice versa. If we double the slice thickness, we get double the SNR. Because we have double the voxel volume, right? Nothing else changed. Field of view stayed the same. Matrix stayed the same. See what happens here. Now we've decreased the field of view, right? Didn't change the slice thickness. We had a 40 field of view. We had a 10 millimeter slice thickness, and our matrix is 4 by 4. So now we have a 20 millimeter field of view. We're dividing that by 4. We have 5 by 5. Didn't change the slice thickness. That's 10, right? How much did we decrease our voxel volume from here to here? Based on the math. Well, I heard 1/2, and that's the tendency to think that, but it's not. Look at the math. It's a quarter of the size, right? Why isn't it half? We have the field of view, but we did it in 2 directions, right? It's now 20 here and 20 here. So we halved it in 2 directions. 2 times 2 is 4, right? So our voxel size is the quarter of the size that it was before. Having the field of view did what to our SNR then? If our voxel volume is 1/4 of what it was originally, it decreased our SNR to 1/4 of what it was before, right? So if your SNR is 100 and you take your field of view from 40 down to 20, your SNR is gonna be 25. Because if you look at this piece right here will fit into 1/4 of this. Right? Field of view has a large impact on SNR then, right? And then matrix. Obviously, if we increase our matrix, we are decreasing the size of our voxel, right? Thus decreasing our SNR. If I double both matrices, if I went from 4x4 to 8x8, what happens to my SNR? Well, it went down, right? Because I doubled. Remember, my voxels are now 1/4 of the size they were before. Because I doubled in 2 directions, right? How many pieces I cut it into. This is where everyone gets confused. If you have a high number of your matrix, you're cutting the whole field of view into more pieces. Thus your voxel volume gets smaller, right? We call a high number in the matrix a fine matrix. So if my matrix is 512 by 512, that's a fine matrix. It means I'm cutting my field of view into 512 pieces on each side. If I have 200 by 200, that is a coarser matrix, making those voxels bigger, right? Which one of these gives me better SNR? Everything else the same. This one, right? It's got bigger voxels, fit more protons in there. Yep, we'll talk about resolution next. Let us take a break. What do you think? Then we'll come back and revisit some of this stuff.
Sorry, question. It might be something wrong with my device.
Yeah.
I'm not getting anything.
You need to download the PowerPoint.
Really? Yeah. And all these slides.
That is, so it looks like you're in you're not looking at it in PowerPoint. You're on the browser. You have PowerPoint on the system? So where is the here, this is customer talent. Folder. Say open with. You might not have PowerPoint on your system. It's just opening it in the browser. You probably have to download, go to like Microsoft Office and try to get a free version of PowerPoint. Yeah. Yeah, because it's showing, it's some browser version of it. It's not really working.
It was opening the wrong PowerPoint for me, but like a green one, but I guess you're like.
Yeah, that was supplemental materials. You gotta open the essential materials. Yeah.
So she's not gonna get, I guess.
it's just like we're called there right now. So we don't really know anything yet. We try to figure out what this kind of thing. Yeah. But like, we're just hoping that she's a kid. So sometimes they all play together. So we're not super, all of them were in the front. Just for herself. But there was just a fire that was really bad. Close by and she was in the way. So I had to be, yeah, I think it had to be her.
It's terrible, man.
We wanna let you know.
Yeah.
It's not here.
Yeah, because I don't know how long she's gonna be. out for.
Yeah, no, I'll let everybody know. Yeah, that's terrible. Where did you come from, you know?
Well, so she moved from San Diego over here. Sometimes she travels back and forth, but I think she was coming from like also here.
Okay.
Her apartment.
All right, I'll let Simone know if you're call right now. Yeah. Thanks for letting me know.
Yeah. Hey, wait, how long was the break?
We'll see. We'll come back at noon.
Noon, okay.
I'm gonna write it down the way you explained it. I should go to the Microsoft.
Yeah, just try to find a free version, like a free PowerPoint viewer.
And then go to the Microsoft.
I mean, it'll probably be with Microsoft Office. I would just search for free PowerPoint viewer, and there's probably a free version of it. It's not gonna let you use it, but you should be able to do it.
Microsoft?
Yeah, it's because it's a Microsoft product, but Office, Microsoft Office.
And then.
Download the free version of it, and then you open, it should automatically open with that if you have it.
Yeah.
Yeah, sorry.
I just had a question, so whatever that imaging you said, like, was it super clear? And I assume we're gonna get there on hard. If this way they're labeled something like P and this way is that.
Yeah, it's
Phase
frequency and phase.
phase and frequency.
Yeah.
Okay.
Yeah, so we're,
They like,
I mean, we're not gonna talk about, what that means 100%. Yeah, it's essentially how are we encoding? We encode with phase or we encode with frequency.
Right.
We encode with frequency in one direction by putting a gradient on that frequency direction. And then we're collecting data points, however many we need to create as many voxels as we want. And then we collect different echoes with a different amount of phase shift, which equals our lines of K-space to give us our resolution in the phase direction. So when we're looking at these, you know, like a 512 by 512, that means there's 512 echoes that need to be collected with different amount of phase shift. That'll be our phase direction and our frequency direction. Every echo we're gonna collect is gonna have 512 data points with different frequencies because we apply that gradient.
and
That's not something we're really gonna get into today.
they're not always gonna be the exact same. Like,
No, we can make,
512,
yeah, and typically, and I'll show you, like, this will come up, mostly it's gonna be like a lower number in the phase direction. Because that directly affects scan times TR times next. So we can have rectangular pixels, which we normally do. We're losing a little bit of resolution, but we're gaining a lot of scan time.
Okay. Yeah, that was talked about too in the imaging, the rectangular
Yeah,
frequency.
rectangular voxel or pixel size, yeah, and it's in the phase direction, typically, so we have the smaller.
Because of the shape of the body, right?
Well, that would be phase field of view, that's different.
Okay.
Yeah, we'll get into that too. Don't worry, we'll get there.
I remember it was saying that. Yeah, I mean, just all the boards, where root boards too, so that means like. Ryan, so do we have two more pieces?
Yes.
Yeah, but that, yeah.
Yeah, that'll be easy, it's only 20 questions and you guys know that. Yeah. I'll be back, let's be back by noon. Noon, yeah, we're taking lunch.
Oh, okay. It's pretty early out there, we had to get out.
Sorry, you're right.
Oh, I just.
I just don't understand what are we looking for here, man? Less SNR, more proton density. We're looking for the picture, man.
Perfect.
But they need to trade off what here, I mean.
Maybe you're not saying, like, curve.
Yeah.
You recorded the.
Yeah.
Can I get that from you now or after we're? It's the main truth. Okay.
I know, I've been. How are you holding on?
I'll send you a text. Send me a text.
I've done well. No, I did. That's what I did.
Oh, yeah. 9855800.
Oh, yeah, yeah. Yeah.
Yeah, so no,
I really like
Want to break down so it's mirrored in one of the probably just so broken down for another 10-15 minutes. Okay, this is the one starting to get a little. Yeah, family. So I remember you'll say like what it can be 0 to that number.
Yes, so bandwidth is how much information something can get, right? So in this case, it's coming in frequency. The smaller the bandwidth, the more frequency the flow.
So is that better? You have a higher.
It just depends. If you increase your frequency, you're only getting more noise. If you increase the XML.
You gotta find sweet spot, right?
Yeah, exactly. And that usually is with lower frequency. With lower bandwidth. Because we're lower bandwidth. So you're getting more frequency and less noise. So that's kind of,
Okay.
increase your bandwidth, you're seeing more signal. So you're.
So you gotta decrease bandwidth, but to the right amount. If you decrease it too much, you're gonna get artifacts.
Yeah.
You're seeing what it is, it just basically makes shit up. Because it doesn't belong. So the noise is so much that it's creating shit. Because it's back.
So what I think is
That's you're expanding the frequency, but you're also increasing the signal. Frequency inference.
So a lower frequency is better.
Yeah, lower frequency.
Oh, this is better. The amount of signal. Okay, cool. I thought you were saying that. You want to hear kind of what you- Okay.
If you have more noise, no,
That's why you want a less bandwidth, right?
yeah, it's focusing more.
But then it's
So you can kind of see it.
I do think, yeah.
Yeah, so the bandwidth you decrease it,
more than 20.
you increase it.
I got
When you
it.
increase it, you're focusing more on more frequency and less noise. But if you're increasing it, you're getting the same amount of noise, so you're expanding it for more. That's why. Yeah, that's what.
You're sending
But,
bullshit to
you
me.
know, that's lower bandwidth. Yeah, yeah, on the wide line, but like that. Which the lower bandwidth also increase, which happens like with, reading the middle connecting to themselves.
I wonder if it's you, because you're like looking, but you're like. I wonder if you can. No.
This doesn't make any sense to me. Okay, or about
Increase the sampling time, which increases the amount of heat available.
yeah,
So if you lower that, that means it takes longer to scan.
so basically, no, your T has nothing to do with it. Your T is what you pick up on your TR. So your TR will be the same, but your echoes will be closer to the end. To the page.
Oh, no, I'm saying like, if you do a lower, bandwidth, are you gonna have longer scan times?
No, because again, it doesn't affect your TR. Your T is inside your TR. So what happening is your T
Maybe.
is expanding.
Drinking coffee.
And you need to like sample it and to get that information. But it doesn't expand your TR for yourself. It's something inside. So, with that said, you kind of understand that?
No.
It's not something you said just, you know, like lower bandwidth.
Coffee in the little file. Yeah.
Voxel value, you know, where it's the way, so this is what it is. These besides the string, the little, you make sure that each fucking text.
Yeah.
From bottom,
Bottom, like
this whole array. It's your X's. Okay, okay, so X and Y, when you look at that, you get 525 by 525.
Yeah.
That's your,
Or whatever it is.
yeah, the lines and the rows. Or, sorry, the rows and the columns. That's what it's called.
She was already.
You see the resolution?
Oh.
Gain more color with each, with the smaller you get, when you gain more boxes, you'll be able to see more. But the less matrix there is, basically the less pixels, the more simplified. So you go from all these different types of colors, I get that with a 4 and four, you know, it's like these 4. How can you get out of it?
Keep up with the next slide.
And I'm already drinking, I'm like, whoa. Maybe it's like I'm like.
Slice thickness is the same thing, it's just basically.
How does slice thickness affect scanned on and the scanning, levers? Slice thickness, get like better, lower, lower.
Do you just? What's my name? I can't say that. A little bit longer. So I just wanted to chill, take an hour, it's like. And I couldn't pause the meeting, there's not.
You're basically.
I will wait.
Yeah, so just that, larger voltage. This is, that's what slice thickness.
So higher FOB has a higher.
Higher is not, because you're picking up more.
Okay, a higher slice thickness. According to that.
Higher.
Then I'll still go with that, like.
Slice thickness is more, because you're expanding it progressively. And then the matrix, so you increase the matrix, which is more pixels, and you're getting more information. So that. That makes sense, so you can go from higher up with expanding. You're covering more surface area. Right, higher
Matrix is higher as well.
so this is what you know, you put in, which is, you see, give us. So you're scanning it, was trying to get information, and there's. Okay. Just becoming double, that's the resolution. Put them small and make them. So the signal will get.
Which ones are those?
The 4 milligrams,
What brand are those?
on the lamb, this one is 7.
What flavor is it?
No flavor. No, because in California, you can't have any flavor you could be.
I thought it's survey, 3 milligrams bigger. Where do you buy it?
Anywhere, San Diego?
Kind of like a law that got passed, but nobody really follows it.
Oh, like, yeah, like head shops.
Yeah.
I just get these at 7 bucks.
That makes sense, they have to like follow the rules that they. I was maybe for a couple of years, like basically, yeah, 2 years or so. Not long. I like it looks like the same way. Like, excited, stuff like that.
Studying and nicotine is really good.
That's why I don't plan on.
These are so bad, they don't keep fading.
Like making up for studying, that's too much at one time, but I can look at the present and it's just like. It used to take me like 10 days to kill a vape, and then by the time I stopped doing it, which was for around years, I was like. So they're kind of what? They're not good for your health. I mean, nicotine in general is a massive diet, or massive constrictor, so it's like you're getting less. Which can lead to that. I don't know if it can experiment though. Experiment when they're green, like a lot of different.
I know, I was trying not to.
You're all. What's
Everybody just looking for
Three.
They come in 3?
I don't think they're higher than 3.
Oh, it's not
It's like the lecture thing and not like the.
Yeah, you don't want to.
Yeah, like
Uh,
whoever.
probably going fine. You want pizza? What's up?
I think so.
Oh, that new. Yeah, thanks for explaining. Get it a lot better now. You haven't seen that with the babes, like last time I took a trip, I was like.
I'm scared to that one. My friend has one and that kind of. And then he's telling them. You know, let me know.
Also, like, because it messed up all the technical, tons of what you did, that jobs are actually counted. So like, that's the reason.
Oh.
People were gonna continue the lecture, and you came out the next week. If they were gonna continue the lecture. I mean, you're gonna say this for them, it's like, living continuation, do this one. Part two is probably gonna get reviewed. Well, I mean, we're on lunch break, so. I wouldn't see why, yeah, caffeine and nicotine, why would he continue this?
That's that.
Caffeine drinking different. So is that the other? Different department?
I'm like.
Just reading something.
You were, memorial care. At no, I'm not getting anyone. Probably walk to a Starbucks, just gonna walk. They just laid off like. He's like, yeah, it's all about the man, little man. Yeah, like, it's like none of the parts of it, I mean, almost, and I just. Lions Hospital. People are educated and happy, so. So doing those pictures.
No, I'm just, yeah, I'm working, every 11:30.
3D. Oh, that's.
I'm a senior person, so. I do,
Emphasis.
yeah. So just like, I feel like, I took the car, the light acting, the sports are, thinking that we know. Personal.
So you just started a job. What happens? 4 or 5 years.
They didn't know that in school, so I'm like, okay, this will go. But I told them, I was like, as soon as I start reading, I'm just doing like this one, open, I'm just taking that. So, you know, I surprised when I start putting. I'm gonna get, wish I was working and I'll do that. No.
Who's dropping? Oh,
Some people that, and so they pretty much didn't want to like, inside of it. That's what I didn't remember. I was like, yeah, I didn't.
Where do you want to get?
And then I remember that interview in because yeah, I was just like, this was like, oh, it's really interesting. I was like, all right, they don't know. No, no, I'm like, no, that's just pretending. I'm not gonna sit here and speak. I know, it's like too much. It was like, it's a big magnet.
I did that a lot. Every time I'm like.
I'm like, it's not good donut, and I'm like, okay, I've had those before, and I'm like, no, you haven't, no, you haven't, and I'm like, you can help, I'm like, you haven't. And then, and then I show them, and then I'm like, did you drop anything in the middle? No, and then yeah, you did. I was like, really, when you say, I'm like, no, it's on my phone, but you've been holding it, you know.
Yeah. I get asked all the time, but the CP, I'm like, I can give you a long answer or a short answer, looking how much you're wanting to know.
I'm like, do you not realize that really like you the walk the most like, it's like you see the most yeah, and policy. Yeah, maybe. I'm like,
It's the end in bagging it.
like it's, I'm like, I'm not even explaining, but I was even.
We're not supposed to even train the danger of something. That's my friends around like. So if I get this involved, this. He's like, film more, it's like, some force where you did your job. So.
We had a long way. I was like, yeah, I'm really doing this shit for the rest of my life. So I was like, yeah.
Not necessarily.
Yeah, I mean, maybe I'll start in this case, but
I think a lot of us are in good place. I think that's probably.
yeah, to be honest.
No, just want to. It's more.
Well, honestly, I know one of the machines is going to one right now. And he's working like 3 days a week, and then one day he works 18 hours, like working in the morning and just yeah, and it was 6 a.m. to 3 and he's an hour but it's been sleeping, and then he was sleeping from 4 to 3 and I'll be out there, I'll do it. And then I'm doing all this. But he's so good.
I think I can.
Like, I don't think I do this whole thing. The next day, it's like,
It's just impossible.
no, but he's not place there, so it's something, well, it's there, and I'm not in a position.
I feel like at one point we just like keep talking about, like after the 10-hour mark, like you don't even, I'm just like, we're on already here.
Yeah. I feel so comfortable. But we should have been doing like homework and really, you just go to home and studies also.
And then it's just temporary, so.
Yeah, that's why I'm like, you got to graduate from May. Yeah, from this point.
Great. Next, let's all be done.
Yeah.
So I know that a lot of people, well, not a lot, but some of them do work 12-hour shifts.
That's what I used to do before this job.
I feel like that's nice.
Well, this is nice, it's not. No, no.
They go crazy for the. Well, don't they like harvest their organs?
Well, it depends on the family. Usually, but they're pregnant, you know, sometimes people are very little.
You know, but like the plastic surgery.
Oh. Oh, yeah.
When they're saying that they're doing like
Yeah, like,
procedure.
She's like, oh, like, if you're all ready, so you know.
exactly.
Camp out there.
That's what I told my mom, I was like, you are fucking right. And we're like, I'm really not just for my relationship, because I'm on my back, I was gonna go to sleep. I thought it was actually, because they're treating me like $5,000 with my insurance. With my insurance. I'm like,
You know, they do a lot of research.
yeah.
Oh, because they're putting you in here.
It only has to be in 4, and then I have to,
You know, like, the additional.
I read it. Yeah, and like you can see them in the X-ray, you can just see them right now, so like that.
And how they sit, the genetic situation.
Yeah. I'm not even gonna do something.
I'll do it out when I was like 13, that I even.
Yeah. This is from here. Someone last year. So they said.
Oh, jeez.
It's like,
It looks like a lobster at first, I'm like, oh. No, this is a different hospital. You know, somebody who did very different. They got their orders.
You can see the red state and.
Right.
And then those things, because we let us like stand right here, and the 2 surgeons were trying to, if the different thing is the job with the heart, so you can just, I can't see them fighting. The older surgeons, you know, have the younger surgeons, no, you can't do this. I'm like, yes, I do. Like, anyway, let me second. Let me like, have to be very careful. I did love sound. Yeah. And like, they were, as soon as they got on the part, it was like, okay, everybody, you did everything else. And when they left, like that. So I was like, compared to them, and stuff like that. I think it's Colorado. And they grew, yeah, and as soon as they found people working. 20 something years ago.
It's just, you know. Our parents have very different.
Oh, man, the whole is different, positive, 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 I'm like, oh.
It's a street drug. You know, it's like-
I'm like, I'll just have you that. That's relaxing. But yeah, I mean, that's crazy. Crazy. I was over here, like, I could do my reading. It's like someone came in. I know, but like, I don't even really affect me, but I like down. Maybe I should.
Say more than 400.
I'm already, did you guys hear about that, an arrow thread in the money or something? Is it in so large, I'm like, it's like, it was so bad, and people didn't know it was meant to be like, a constitution. They were drinking. Meal, and before I was like really fat, like, it's going to be ER. I didn't do that. It's like one of the drinks that they have at your. Apparently it's really good, those is people really go on. Yeah.
It's like, just even if you feel like. What's
So when you have to mentally, it's not like, it's not big, don't back me.
And you're just like,
Yeah, my leg goes like this.
I know.
I know, it's all there, but sometimes I just have to sip it a little bit. It's like shaking my seat. Yeah, I'm gonna go out to do that.
It's like sleeping.
I was like, yeah.
Yeah. That's the one I kept opening up. I was like, why is it not the same one as this one? That's why Katie opened her computer, because I was like, I don't see it, and she tried to look for it too.
Oh, I know what you're talking about. I pulled up to a screen.
This one, like six.
I think it's the same thing that's done by someone else.
Maybe that could be it.
The same word is.
I think it's like a bold point version.
Yeah, because I was trying to follow along, and I was like, wait, that's not the same PowerPoint. Okay, maybe not then. But it's only like
That's why it's under someone.
21, 25, 35.
ER.
Maybe there was a limitation that tells you to do
Yeah, but that's. Yeah, I think it's not.
One section I was down, well, right now I'm doing CP, I'm like, one of the CP was a big one, so I'm like, hey.
Yeah, first and
Yeah.
Done.
I might go over the MRI afterwards just to see what it's doing. So I don't like.
I just, see if I can, maybe get rid of some. Like diabetes, I'm still waiting to explain.
No, me too, we never got one every else after I got one.
After.
So I didn't have any diabetes. For real. So like, I do a whole work, like, from that, yeah, but even though they're like, where's my shit? I don't know what. I know, I would, you know,
It's kind of like Reddit, I was talking to about.
yeah.
Yeah, but I thought you were gonna be able to partner with us. Oh. You don't know anything? Is that like?
It's gonna start in for MRI.
Okay. Like 2 weeks.
Right after we.
I already. Oh, it's all on MRI, subreddit? Yeah, yeah. And you start catching my college thing. And you told him? Yeah. He was listening about it. I saw a similar comment to college is. You might have got.
Maybe we did.
Yeah, one day when he was like being nice to us. That whole crazy.
Yeah.
He was like, I feel bad for them. They've already been through enough. Maybe they don't have a
It's
teacher.
the college has a rad tech program.
I'm trying to add like.
It's an X-ray tech and it's 5K, but it's a lottery system.
Yeah.
Well, a lottery system. So your name's in there and they.
Yeah, if you try.
Bunch of names.
I mean, I would like.
They can be up to like.
Like, we can go through it over.
Yeah, because I mean, next year.
The team on this stuff, same share, there's no way you'd want.
No, like, we're not gonna be on the same class. We're just gonna record it and send it to us. And then we can review or whatever we.
Probably get more. Like, I'll offer you the part.
Passwords.
You probably get a better chance of getting in the program.
Do you know how they?
50K down. So there's a good thing for you. We honestly probably get a lot of.
Where you can come if you want to. It's like, oh my God.
I'll put my name in there. Maybe you can write this program. Down the line, you see that. I'm taking a 1 year class now. Upgraded. Making my own distillery factory. Launch MRI. Yeah. Make $1 million, not. I bought his winery this. Yeah. So I want to get back to surgery.
Saying how,
So basic college, basic college have an X-ray tech program for 5 years.
Yeah.
But it's hard to get it. I've tried.
Didn't they call you?
Right after like.
That was too much.
Oh, yeah.
He might get, he might buy everything else.
How did you get in on the wait list for?
Pima?
Like, you know, Mesa?
Mesa, it was too difficult.
To get in?
Yeah.
I thought you just had to like put in your name.
No, it's on. It's easy to get in Pima.
What's wrong with how hard is it in Mesa? Like, what does it make you do?
The long waiting list.
Yeah, I can probably wait.
Why you do?
I didn't know that's true, right? Compared to Jamie.
We have pretty in-depth.
We have pictures.
Yeah.
It's studies statistics beforehand.
Hey, Brett. I want to apologize, Jimmy County told me off because I worked last night.
Oh, yeah.
So I'm kind of like you see him around outside. So I usually get Fridays off,
Yeah.
and I have it, but last night I couldn't get off, so.
That's awesome. Do your best, man.
Oh, yeah. I don't know, the cops are on the place.
Yeah. Probably material too.
Yeah, that's awesome, though. I love it, love it.
Good.
There you go. Take a picture of myself. Try to get that over with, so it's more. Yeah, so he's making everything inside. Get another copy, so, but she's not. And like. I have to make $1,000 in New Year's. That's what I want to go. Yeah. The stuff from my. I haven't seen that. I heard you said about your dog. My actual sister, so this must get it. People say like Southern has COVID that's weak. No, that'll give you more. Yeah.
We're ready? Might have to just call it. So it's a good time to, well, first of all, ask if there's any questions so far about S&R. I mean, I know it's a lot of material, but if you come up with anything while you're at lunch, you know, the brain started working, like, oh, wait a minute, I'm not sure I understand this, and then it's be a good time to ask. You know, we're not done yet, we gotta keep going, but, a majority of it has already been discussed. We good? Nothing you wanna ask yet? All right, and another thing, let's revisit multi-slice acquisition. I know we talked about it in, I think, week 2 or 4. Does anyone remember what that was? It was in the PowerPoint. We went over it, but I didn't test you on it, so maybe some of you have forgotten. Essentially, multi-slice acquisition states that we have to collect one echo per slice in a TR period. Right, so right here is our TR, correct, from here to here is our TR. And all these slices have that TR, but we have time, right, in between waiting after we collect this echo until we have to go back and excite the next slice again. So in this case, we have time to, collect data for slice 2, 3, 4, 5, 6 until we have to go back. So in this case, with this TR, whatever it is, and the TE that's prescribed, we can collect 6 slices, right? So keeping this in mind, there's another trade-off involved with your TR, right? Right now, we know the shorter the TR, what happens to our contrast? If we lower our TR, what happens to contrast? Can't remember. What does TR control?
T1.
T1 contrast. So what happens if we lower the TR? Increases T1 weighting, right? So we get T1 weighting with lower TR. So we get better T1 weighting to a certain point. If we decrease it too much, then it's bad. What is the negative trade-off of reducing the TR? It lowers our SNR, right? And another thing it does is lower the amount of slices available, right? If I needed better T1 contrast here and I wanted to lower the TR a little bit, I'm losing SNR, but I'm also losing the ability to scan this slice, right? So that's something you got to consider with your parameters as well. You could potentially need to balance, the amount of slices you have available per TR that you want. Also, TR affects scan time. I haven't talked about that yet, but we'll get there. TR times next times phase matrix is our scan time. So if we do end up adding more slices, because we do have to cover through the entire area of interest, right? We can't say, oh no, 5's fine. We just won't get, the bottom of the brain or whatever. We still have to cover through it. So adding more slices might require us to increase our TR. Right? So what's that going to do to our scan time? Increase it, right? So more trade-offs you got to think about. So scan time doesn't have anything to do with the amount of slices. It's really just TR times next times phase matrix. But you can indirectly impact your TR by adding more slices. And you can indirectly impact the amount of slices available to you if you decrease your TR. So some more things to consider. You might want to jot down by your TR in that little triangle there. So all of that was about SNR. I know we talked about more things as well, because I wanted to, kind of get you guys to understand how everything relates instead of just jumping around. But how do we maximize SNR? We wanted to get the best SNR ever. We want a long TR and a short TE. Obviously, that's not always the best case scenario, because we're not gonna, what kind of contrast do we get with a long TR and a short TE? PD, right? This kind of tells you right here, PD is gonna be the most signal heavy. Right? But we want to get T1 and T2 weighted image as well. So that's not always going to be the scenario. 90-degree flip angle with long TR and the Ernst angle with a, sorry, that should say short TR sequences. Ernst angle and a short TR sequence. The correct coil in the proper position. Low matrix or coarse matrix, right? What does the coarse matrix do for us? Gives us larger voxels. Gives us larger pixels, right? Which in turn is larger voxels. Large field of view gives us larger voxels as well. Thick slices, larger voxels in the depth area, right? High necks and low or narrow receive bandwidth. So of all the things we've talked about, that is what gives us the best SNR. But it's a trade-off, right? We're not always trying to get the best SNR. We're trying to trade it in for other things that we need as well. There will be some scan math about voxel size, pixel area, and voxel volume. What 3 parameters control our pixel area and our voxel volume? There we go. I heard it. So voxel volume. Controlled by three parameters. One of them is split into two different ones. We have our field of view. Think about the field of view as like the size of the picture you're taking. You're gonna have larger fields of view if you're going through larger anatomy, right? If I have to do an entire femur, it's a pretty large field of view, at least in the coronal and the sagittal plane. Axial can be smaller, right? Head is gonna be smaller. If you're doing a wrist, it's gonna be a much smaller field of view. So think about it like as zooming in or zooming out, kind of just to encompass all of the area that you need to scan. Matrix is how many pieces you're cutting that field of view into to give you the voxels that you need to get the resolution that you need. We'll talk about resolution in a second. Matrix is comprised of two different matrices. We have frequency and phase. So our matrix, there's two different directions in our field of view, right? So we have to cut them into different pieces, and we can do an uneven matrix. We can do a larger frequency than a phase if we want, which we'll talk about in just a second. But we need to do our field of view divided by each one of these, multiplied together, and then what's the last parameter we're looking at for voxel volume? Slice thickness, right? So if you're given these three things, which is four numbers, because matrix is two different directions, right? You should be able to figure out voxel volume. And if you're given these two, you should be able to figure out pixel area, right? Does everyone know the difference between area and volume? Area is the amount of space in two dimensions, right? So how much area does this tabletop have? We just multiply this side by this side, it gives us our area. If we want to know how much volume or how much three-dimensional space it takes up, we have to add that third dimension. So we multiply it by the depth and the thickness of the table, right? So be careful. The quiz is going to ask you find pixel area or voxel volume or both. You need to know the difference. So let's say I have a field of view of 30 centimeters. I have a frequency matrix of 320 and a phase matrix of 192 and a slice thickness of 6. Slice thickness is always going to be in millimeters. So if your field of view is in centimeters, you want to get the units the same, right? You want to have the same units to do this type of math. So let's say we need to find the pixel area. How would we do that? That's what you should do first anyway. If you're solving for voxel volume, first find your pixel area. What it is field of view divided by one of the matrices multiplied by the field of view divided by the other matrix. So find pixel area, you do FOV divided by frequency, and it doesn't matter which order you do this in, times field of view divided by phase. We want to get it in millimeters. It's in centimeters right now, so how do we easily get it in millimeters? I'll give you a hint, there are 10 millimeters in a centimeter. So you just add a 0, right? Just multiply it by 10. So it'll be 300 divided by something times 300 divided by something else. Frequency, what's my frequency number? 320. And my phase number is 192. Right here, the answer to both of these is going to give me the dimension of the pixel in each different direction. So could somebody pull out a calculator and give me the answer here? What's 300 divided by 320? It's less than 1.93. 0.93, and that's millimeters, right? We're literally taking a 300 millimeter field of view, dividing it into 320 pieces. Each one of those little segments is 0.93 millimeters. And we multiply that by 300 divided by 192, 1.56 millimeters. Obviously, we're cutting it in less pieces. It's more coarse on this side. So we're gonna have rectangular voxels, which we can, it's fine, and we do. Just less resolution in this direction than in this direction, right? To figure out pixel area, we just multiply those two numbers together. What do we get? 1.45? That is 1.45. Thank you for doing the math for me. And it's millimeters squared, right? Because we're looking at little squares or rectangles in this case. 1.45 square millimeters. So in this case scenario, if I selected a 30 centimeter field of view, my frequency matrix was 320, my phase was 192. If I zoomed in on each one of those little pixels, this is the dimensions I get. 0.93 in one direction, 1.56 in another. You multiply those together, that gives you your area. Not too tough, right? Hopefully. And you can use a calculator to do this. You just have to remember, get your field of view in millimeters. It might be given to you in millimeters, but if it's not, make sure you get it in millimeters. So just add a 0 to the end. Right? And if it's like this, say this is your field of view. Right? How do I get that in millimeters? Just move the decimal place over. Right? You're just multiplying by 10. I've had people before just add a 0 to that, and that doesn't work. So just multiply by 10, move your decimal place over. It's right here, you gotta move it over, you gotta add a 0, right? The next thing you do is just divide each one of those fields of view. The field of view is gonna be the same, because it doesn't change, it's the same in each direction. It's a square field of view divided by the frequency matrix. Get that number, divided by your phase matrix, get that number, multiply those together. That is your pixel area. Got it? All right, now how do we find out our voxel volume? We take our pixel area and we just multiply it by the third dimension, which is our slice distance. Okay, you take 6 millimeters times 1.45 millimeters squared. What do we have? 8 something? What is it? There's two numbers multiplied together. 8.7. 8.7, and that's millimeters cubed, right? We have square here multiplied by another. Now we have little cubes that are that size. 8.7 millimeters squared, or cubed, sorry. And that is your voxel volume. So you will be asked to answer questions like this. If give you those numbers, you should be able to figure it out. And this kind of determines, you know, if we're looking at this, we can kind of figure out how much SNR we have, right? If this number went up, would my SNR go up or go down? Your voxel volume gets bigger, the SNR goes up proportionate to the amount bigger that it got, right? So if I doubled the size of this voxel volume, went to 17.2 or 17.4, then it would, we'd have double the SNR that we did here. Pretty easy, hopefully. Hopefully. Just practice on your own. Just give yourself different values, you know, and I do have, I think in the chat, there's definitely a chat about it too, so you're gonna have to do some math in there. Anyone want to do one more? Field of view, 180 millimeters. Matrix frequency will be 384. 224. Slice thickness 3. What do I want to do first? Give me pixel area. Field of view, which is 180, it's already in millimeters, I don't need to make a change, right? I'll put that up there twice. And what do I divide it by? 384 and 224. What does this first one give me? 180 divided by 384 is 0.46, 0.47. And what's 180 divided by 224? 0.80?
Yeah.
0.8. Then you just multiply 0.8 times 0.47 to get 0.38 millimeters squared. That's my pixel area. To get box of volume, we take that one, multiply it by our slice thickness. .14. Much smaller than our last scenario, right? And the reason for that is threefold. Field of view is much smaller. It was 300 millimeters before, right? So we shrunk our field of view. Our matrix is finer. It was 320 by 192 before. Now it's 384 by 224. So we're cutting it into more pieces. Cutting a smaller view into more pieces. And then we have half the slice thickness, right? So before it was 8 something, right? 8.7. Now it's 1.14. That's because thinner slice, finer matrix, smaller field of view. Better or worse SNR than that first scenario? Worse, right? The reason we have the matrix divided into 2 pieces called something different has to do with the way we spatially localize. We won't get into that until physics 2, fortunately, because it's a whole other thing. But just know that if I have a field of view, I have 2 different directions, right? I have to cut one of those into a certain amount of pieces and the other into a certain amount. And we call them frequency or phase, and you can swap them. You can make one the frequency and the other phase and swap them out. It's up to you as the operator. The reason for that is for spatial localization and the physics behind that, but we won't really get into that yet. You just need to know that there's a difference. And the reason you need to know a difference is because the phase matrix affects your scan time while the frequency matrix doesn't. Bada bing, bada boom. Contrast the noise. Don't spend too much time with this. We talked about how TR, TE, and flip angle affect SNR and also contrast. That's really what I need you to know. Contrast the noise is just sort of saying how much SNR do I have between adjacent tissues. If I have a lot of SNR difference between different tissues, I have a lot of contrast to noise. Like right here, dark and white, right? Black and white, essentially, that's a lot of contrast. And these parameters are basically your TR, TE. You can see what's going on. Does anyone know what we're looking at here? Yeah, it's the biliary tree. It's a MRCP that we're doing. You're looking at the gallbladder. You see your pancreatic duct, hepatic duct, common hepatic duct, right and left, and then the common bile duct. But yeah, we do. That is a scan in MR that we do. Hot, heavy contrast that has a very high TE to make everything else dephase but keep the fluid still bright. Right here as well, that's a lot of contrast, that's a torn glute muscle right there. Right, a lot of contrast, you're not seeing a lot else, but you can see that tear, it's all this edema here in the tear. The fat suppression of the butt cheeks. But you can see what's going on, right? There's obviously a tear right there. Good contrast to noise. Once again, controlled by TR, TE. Don't worry about all of these others. We'll talk about them later. So on the opposite end of SNR, at least as far as these 4 parameters, we have spatial resolution. Spatial resolution is essentially inversely proportional to the SNR in terms of field of view, matrix, and slice thickness. The smaller the pixel or voxel, the better the spatial resolution, right? In regards to SNR, the larger the voxel, the better the SNR, right? So if I have my pixel size or my voxel size, I'm gonna get half the SNR, but twice the resolution. That make sense? Hopefully this will help you understand what resolution is. I mean, everybody has seen high def TVs before. The reason they're high definition is because if you're looking at this TV, there is literally a matrix here that's so hard to see because it's so small. It's being cut into pieces in this direction and in pieces in this direction to where there are little squares in here that all have one color associated with them. You can see it right here. This is a low resolution coarse matrix. We could literally count the amount of pieces this is divided into because we can see all of the individual pixels that it creates, right? Which one has more detail? On the right. 100% this one, right? We can see a lot more detail here than we can here. Same thing with MRI. We get smaller pixels and smaller voxels, we're gonna have much better detail, much better resolution. High resolution picture, I can't even count the amount of pieces this one is divided into. This one you could literally go and count and figure out what the matrix is. So a very fine matrix, very high number on your matrix, very low matrix, the field of view is exactly the same, right? So once again, the matrix and the field of view determine the pixel area. We have 2 different dimensions, the phase and the frequency matrix. Right here, we have 256 by 256 by 512 by 512. This is a little bit deceiving because as I pasted these pictures on the PowerPoint, it made its own box pixel sizes, but you can, if you zoom in on this, you can see the pixels here and you can't here, right? Problem is when you zoom in even further, they kind of go away. This one looks pixelated and this doesn't. But there are algorithms on MRI machines to where if you zoom in, it won't let you see the pixel, it just like kind of smears it and does like a Photoshop to it. If you turn that algorithm off, you would be able to count the voxels or the pixels. But you notice the difference, right? So this right here, I'm cutting the field of view into 256 pieces in each direction, and this one 512 in each direction. You can tell the resolution difference. If you zoom in, look at how blurry this is compared to that side. Much sharper detail than you get over here. So typically words that we use to describe resolution or an image that doesn't have resolution, we'll say it's fuzzy, blurry, not enough resolution. If it's fuzzy or blurry, we need to get better resolution. We need to make our voxels smaller. Does that make sense? So if it doesn't have enough resolution, we need to make our voxel smaller. There's a few things we can do. We can shrink our field of view, right? We can keep the same field of view and make a finer matrix. And then through plane resolution is dictated by slice thickness. We can make a thinner slice. The trade-off though is SNR, right? Getting better resolution, your direct trade-off is lower SNR. And it is a 1-to-1 trade-off. So if I want to double my resolution, I'm going to halve my SNR and vice versa. You can see right here. This actually, you can see the trade-off. Here is same size field of view, 256 by 256 by 512 by 512. You can see the resolution difference. A couple places you can really see it. Look at the gyri on the cerebellum. See much better detail there than you can here, right? It all kind of blends together. But this one looks a little more grainy, doesn't it? That's the trade-off right there. This one definitely brighter, not as much grain. That one more detail, but definitely less S&R. So that is the trade-off in action. Honestly, this one looks fine. I would prefer this one. I'm not the radiologist, but I think the radiologist would agree. And I don't have it in the PowerPoint, but I'm going to show you this one. Slice thickness. Which one of those looks more crisp? Fine detail. The one on the right, obviously, right? There's no change in the field of view or the matrix here. It's just the slice thickness. So which one has the thicker slice? One on the left, right? This is called partial volume averaging. There's a lot of stuff that's over here that's getting averaged with the stuff up front. It gets all projected onto 2 dimensions. And you can see, I'm seeing just basically a ton of different detail all projected together into one 2-dimensional plane. And that is called partial volume averaging. And if we look here on my mouse, I believe it's a 2 millimeter slice versus a 20 millimeter slice thickness. The 20 millimeters versus 2. You can obviously see the difference, right? Which one has better S&R though? The one on the left, but this is not diagnostic. You would never do a 20 millimeter slice in the brain. Right? Much higher diagnostic quality. It has plenty of S&R anyway, even though this one's going to have more, but this is low resolution. And the type of resolution, to get fancy with it, it's called through plane resolution. The plane is a flat surface, right? When you're looking at a slice, you're looking at a plane. You know, you have your scanning planes. Through the plane is the slice thickness, going through the plane. The other type of resolution is your in-plane resolution. So you have 2 different types of resolution, through and in-plane resolution. In-plane resolution is determined by field of view matrix. Through plane resolution is determined by slice thickness. But which one of these has larger voxels? One on the left, right? Much larger voxels, lower resolution, higher S&R. Show you again. Field of view 240, right? Or sorry, 24, it's in centimeters, so it's 240 millimeters. Frequency matrix 256, phase matrix 128. So we have anisotropic voxels and a slice thickness of 5. We could do the math and figure out what our voxel volume is here, right? If we wanted to. So why do we have one matrix that's smaller than the other? That is because your phase matrix is directly proportional to your scan time. There we go. Imaging matrix. An imaging matrix can be anisotropic. Isotropic means the same on all sides. If I have a field of view and I'm cutting it into equal parts, I get a isotropic square pixel, right? If I am cutting it into an uneven amount of parts, the side that I'm cutting it into less pieces in is going to be longer. So I'm going to have rectangular pixels. Your small dimension is always going to be your phase direction. So if you see 2 different numbers on there, if it's 512 by 256 or 256 by 192, the smaller number, the coarser matrix, is always going to be your phase matrix. And why is that? It's because there is a positive trade-off. Lower resolution in this case is going to not only give us more SNR, but it is going to give us a better scan time. That is your scan time equation right there. TR times phase matrix times next. Equals scan time. So we can start to see some other trade-offs as well. If I lengthen my TR, what is the trade-off? Higher scan time, right? What else? Decrease in T1. What else? That's increases SNR up to a certain point. And then what else? Think of multi-slice acquisition. More slices available, right? So there's 4 things. If I increase my TR, I get higher scan time. I get higher SNR. I get more slices available. And I get less T1 waiting. You should eventually be able to just pull these out of your brain. Right? Make one change. This is all the stuff that's happening. So I suggest starting to do that right now. PM is phase matrix. What happens if I change my frequency matrix to scan time? Is it part of the equation? Nope, nothing happens. Frequency matrix doesn't affect scan time. That's why when we're looking at our matrices, we're always going to have a higher number in the frequency direction. We're going to lose a little bit of resolution in our phase direction, but what are we getting back? Scan time, right? Following me? I think everyone's asleep. The reason this affects scan time is because it has to do with case-based and resolution. Remember, case-based, it has a bunch of lines. We have to fill all these lines with an echo, right? The number of lines we have to fill is determined by phase matrix. So the amount of echoes that I have to collect to get that resolution is determined by the phase matrix. I collect 1 echo per TR, right? So the time it takes me to collect that many echoes is going to be my scan time. And then in addition to that, what does next tell me? How many times I fill each one of these, right? So I have to fill 1, 2, 3, 4, 5, 6, 7, 8 echoes in this case, right? It takes me 3 seconds to fill 8 echoes, and then I got to do it 2 times. That gives me my scan time right there. Amazing. So, point being, that's why your phase matrix is always going to be the one that's smaller, because it does affect your scan time. And the reason it affects your scan time is because it's directly correlated with how many echoes we need to collect. And the amount of echoes we collect are determined, or how long it takes us to collect an echo is determined by TR, right? And how many times we fill each line is determined by next. So we could say, like we were doing this earlier, what are the trade-offs here? This is my phase matrix. It was 256. And I reduced it down to 128. What are all the trade-offs for that? Phase matrix was 256, and then I decreased it to 128. What happens to scan time? It does what? It decreases, right? By how much? Yeah, scan time goes down by 1/2. Because this number is half of this number, right? So scan time goes down 1/2 of what it was before. What else happens?
SNR goes down.
Does it go down?
The size of the box.
Bigger. Remember, I'm cutting into less pieces now. So that voxel gets bigger, right? So SNR goes up by how much? Goes up by 2, right? It doubles. Since the voxel size doubled, the SNR doubled. What else happens?
Resolution goes down.
Does, by how much? Why, it goes down because the voxel's bigger now, right? It's half of what it was before. In that direction. Anything else happen? A lot of trade-offs though, right? It affected our resolution, our scan time, and our SNR. The 3 big things in your triangle that I had you set up, right? And then the opposite happens. If I increase my phase matrix from 128 to 256, my scan time doubled. My SNR went to half, and my resolution doubled, right? What happens if we did the same thing with the frequency matrix? Didn't change anything except for the frequency matrix. What happens? What are the trade-offs? Anything happen to scan time?
No.
Nope, nothing happened to scan time. Good. What happens to SNR? How much? 2 times, right? What else happens? Resolution, right? Goes down to 1/2 of what it was before. Why didn't it affect scan time? Because it doesn't affect scan time. We collect all the data for our frequency matrix during echo collection. So we get everything we need in one echo for our frequency matrix. Scan time, shortest scan time would be shortest TR, right? The coarsest matrix possible and the least amount of next possible. But obviously, all of those things are going to have trade-offs, right? This is going to make me have T1 weighting. More T1 weighting, it's gonna lower my SNR. It's gonna lower my SNR. This is going to build my SNR back up a little bit, right? But it's also going to cause me resolution. I'm gonna have resolution issues if I do that. We're not going over any of this other stuff. This will be next week. This is in your book. If this helps you, if you can memorize charts like this, if you have some like photographic memory, this will help. I recommend not doing that because I can't, but if you can do that, more power to you. We will talk about phase field of view next week and oversampling and undersampling, but I want to kind of get you to understand what you need to know for the test. It is a difficult test. People typically do horrible on this test. So study, please study. We're not getting ready to leave yet. I'm going to talk about some of these questions that you might see. I might give you a set of parameters and ask you to tell me which one has the best SNR. So
Which one of those has the best SNR? We got 1, 2, 3, 4. What am I looking for? Next doesn't tell me anything, it's all the same, right? I'm looking for voxel size. I'm looking for the biggest or smallest voxel for SNR. Biggest, right? Here's my trick, field of view has the biggest impact on it. Go to your field of view. Which one has the largest field of view? 1 and 4, right? I don't even look at this anymore. These are gone. Look at the slice thickness. Both are the same. That doesn't tell me anything, does it? Look at the matrix. Which one has the coarser matrix? 1, right? Largest field of view, coarsest matrix, slice thickness doesn't say anything, either does next, right? Number 1 it is. This has the best SNR out of all of these that I picked, that I put up there. Look at field of view. Go straight to your slice thickness. Look at your matrix. We want coarse matrix, thick slice, large field of view. And then if there's 2 that are exactly the same, then your next is going to determine it, right? The highest next will determine that. Which one of those has the best resolution? Out of all of them up there. 3. Look at this. Smallest field of view. Thin slice. Fine matrix. If we did the math on this, this voxel volume would be much smaller than any other on here. You could literally do the math if you wanted to, but you don't have to. This has a much smaller field of view than 18 or 30. Right? We already know we're on the right track. We're like, maybe it would be close. No, it has a super fine matrix, right? And a really thin slice. Highest SNR, highest resolution. Lowest SNR. Lowest resolution. There will be questions like this. I'm not going to say the matrix is going to be the determining factor. Might not be. Use my trick. Look at the field of view first. The field of view might be over here though. Can we list it out in a different way? Look at your field of view. That's going to be your biggest help right there. And then break it down by matrix, slice thickness, and if it is S and R, we're talking about looking at your next. Does next have anything to do with resolution? Did I just give this better resolution by doing that? Hell no. Resolution is affected by voxel size. Does that change my voxel size? Not at all, right? We decided to raise our receive bandwidth from what happened? Always go to the triangle, but then think of other things outside the triangle. What happened to our SNR? Anything? SNR went down. Why? Because our noise went up, right? Anything happen to scan time? Not directly. Did anything happen to resolution? No. But remember, we have artifacts and other things in there too. What happened to artifacts?
Lower the chemical.
Yeah, chemical shift. Does it get better or worse?
it decreases. If I'm raising the bandwidth, I'm putting more frequencies in a smaller area, bringing fat and water closer together. The chemical shift artifact goes away or decreases. Anything else happen? Sample time goes down, therefore, my minimum TE goes down, remember? What happens physically in the scanner? What's going on in the scanner at this point? We raise the bandwidth, that's just putting a number on the machine, but what's happening physically inside the MRI machines? Something about the gradient. Yeah, we get a steeper gradient, so our frequency encoding gradient, frequency, like our frequency matrix, our frequency encoding gradient gets steeper. Be careful. I'm gonna ask you, what doesn't happen if what does not happen if TE is increased from 60 to 100. So if you can tell me what does happen, you should be able to pick out what doesn't, right? So what does happen? What happens if we increase the TE to 100 from 60 to 100? SNR, I think I heard it all in there. SNR goes down, right? What else happens? T2 contrast goes up. Anything else? Anything happen to resolution? Anything happen to scan time? No. There are some other things we'll learn later, but this is all you need to know for now. What does not happen if TR I want to say what does happen. Is the whole list. What happens if we do that? We take our 3000 TR, we move it down to 700. SNR does what? SNR goes down. What else happens? Scan time goes down. There's a couple more. Number of slices, right? Number of slices, what happens to them? Goes down. What else happens? T1 weighting goes up, right? Anything else? That's it. See, this is easy. For you. I know it will be though, but you gotta keep doing it. It's gotta go over, you gotta study. It's not gonna come overnight. Spend several days on it. Like I said, memorizing this can help, but it's not going to be easy. Understanding the concepts behind it is gonna make it much easier. So there's gonna be questions like this. I'm scanning a patient's brain. I'm gonna give you scenarios. I'm scanning a patient's brain and the images look fuzzy. Which one of the following changes will help me alleviate the issue? If it looks fuzzy, what's the problem?
Noise.
Hmm?
Low resolution. It looks fun.
Low resolution, there we go. Fuzzy means we don't have enough resolution. Blurry, fuzzy, they mean the same things. Don't worry, I put in the test, low resolution. What do I need to do?
Increase resolution.
If I have low resolution, I need to increase resolution, right? I don't want to do anything to SNR. I don't care about SNR. I just want to get better resolution. That's gonna make me have worse SNR probably, but how do I get better resolution?
Matrix. Smaller boxes.
Better res equals smaller voxels. And how do I get that? Field of view down, matrix up, slice thickness down, right? If my image is blurry or fuzzy and has low resolution, this is what I need to do. And I'm gonna give you a bunch of options. I did this, and this, and only one of them is gonna be one of these things, right? Might increase the TE, I might do something to scan time, I might change the bandwidth or something, but this is the only thing that's gonna matter as far as resolution, right? I might actually go the opposite way and increase the voxel volume. Is that gonna work? Oh, that's gonna be the wrong answer, right? Want to decrease that voxel volume to get better resolution. Might say this image looks too grainy or noisy. Then what? Yep. If it's too noisy, we need to get better SNR. And how do I do that? Increase FOV, decrease matrix, right? Make a coarser matrix. Increase slice thickness. So the matrix one always confuses people. They see a high number on there, they think that means big voxels. It doesn't. Always think about like a square pizza or a square birthday cake. The more pieces you cut that into, the smaller that little piece is gonna be, right? So the higher the matrix I have, the smaller the piece gets. So if I lower my matrix, my SNR is gonna get better. What else though? This is not the only thing that controls SNR. What else can I do? What about next? Increase. What else can I do?
Lower vision.
Yep. Lower TE. Higher TR. Receive bandwidth. Lower, right? A lot of stuff we can do there. So I can give you, oh, we need better SNR. There could be a bunch of different ways we could do it, right? But it's only gonna be one of them. There'll be 4 choices. One of them gets us better SNR. The rest of them do something else. Or they might even get us worse SNR. You don't want to pick that one. Yes.
How do you make that decision when you're looking at the interface, which one to change?
It takes a lot of practice, man. It's muscle memory, it's playing around a lot, it's experience, it's not gonna come overnight. I was fortunate enough to be at the site. Well, first of all, I knew this stuff like the back of my hand when I went to my external site. And I wanted to play with it, and I had a cool tech. I was like, I think I can get us a better scan time without messing anything up. He's like, go for it. And if it worked, and we were happy. If it didn't, we fixed it. So. It does take experience. Your scanner is going to determine how the protocol is built to begin with is going to determine it. Like typically the protocols that come out of the factory are overbuilt. Like they have so much SNR in them. They have so much resolution. You can cut things down and make changes to get it faster. You can make a lot of changes. They build them where it's like you can just run it and it's good. But typically they're too long because they're just overbuilt, right? That's why you have an app specialist come in and make corrections and make it fit your needs. So. I've seen protocols before where I was able to like almost half the scan time and it still looked fine, still looked great. Yeah. I'm gonna tell you, most of the things you do are to make the scan time better. The business, right? Time is money. And as soon as you get behind, which you will, because you'll have a claustrophobic patient, then you're behind for the rest of the day unless you can figure out how to catch up. And it's pretty stressful. That's why we make decent money. But you gotta know how to do it without sacrificing quality. That's the thing, right? I can fix scan times. I can have all my phase matrices, but then what? What's the problem with doing that? I could lower my necks, I could have my phase matrix, what happens? My SNR is now crappy and my resolution's crappy. Did I do the patient an injustice? Maybe, right? The radiologist is gonna tell you that. You wanna make sure that the radiologist can still read it, you're still providing patient care, but that you got the job done in a good amount of time. What else? Yeah,
Is TE ever used to calculate scan time? And
No.
there's a mistake on the, imaging view quiz, so
really?
TE was used to calculate one.
Are you sure it wasn't echo train length?
No, this-
No, I mean, wasn't it, because, okay, the imaging U thing brings in something called echo train length, which we're not gonna talk about until physics two.
the TE was 100, and if you use that with the calculation, that will give you one of the answers that was on there, and TR was none of the answers on there.
Really?
I
I
got
have a
100%.
question, do you want me to read it?
Yeah.
Says, if I have a fast spin echo sequence with a TE of 100 ms, TR of 3700 ms, ETL of 25, two signal averages, 30 slices, field of view of 240 millimeters, and of 512 times 512, what would the resulting scan time be?
It's just giving you too many parameters.
Yeah.
You have TR,
Yeah, but if you use TR in those answers, it's not.
are you sure?
I'm positive.
Let's do it right now.
Wait, okay.
What's my TR?
TR 3700.
Here, but it's not like.
3,700 milliseconds. What is my phase matrix? It gives you a matrix, right? It says like 512 by
Oh yeah, 512 by 512.
512, so it's 512, right? If it gave me a lower number, that would be the phase matrix. So keep that in mind. If your matrix is anisotropic, the lower number is always your phase matrix. No reason to go higher in phase than lower in frequency. It doesn't save you anything, right? The phase matrix is 512. What is my next? Or averages? Two?
Two signal averages.
And does it have an ETL?
Yeah, 25.
Yeah, we'll talk about ETL in physics too. It's for fast spin echo. I don't want to get into that yet. We do this first. So TR times phase matrix times next, and then it's divided by your echo train length. We'll just do it, you know. This is 3.7 seconds. Right? A millisecond is a second is 1,000 milliseconds. You just divide by 1,000. 3.7 seconds times 512 times 2, all divided by 25?
Yeah.
Okay. So, let me use my calculator.
Right.
3.7 times 512 times 2 equals 3,788.8 divided by 25 equals 151.552 seconds. That's seconds, right? So how do we get minutes? Divided by 60, right? Which equals 2.5258 minutes. How do we get that back into seconds? Because we don't talk about minutes right there, right? So it's 2 minutes. And multiply this by 60. About 32 seconds. Is that an answer that they allow?
Yeah, it had 2.5 and 2.1 and 2.1. So 2.5.
It had 2.5 and 2.1?
Yeah.
Oh, yeah, then it's 2.5. Yeah, if you're rounding it to there. He didn't get it in seconds. So yeah, it would be 2.5 minutes.
No, I got the right answer. You did a different formula in PE. I don't know how I did it.
Amazing coincidence. That's awesome. Yeah, so sorry about that. I'm trying to use imaging you as best as possible because it does help to some degree, right? Getting you kind of used to like at least what we're talking about before I blast you with all this crazy stuff. But yeah, they are talking about fast spin echoes, which we won't get into. So for now, scan time does not include echo train length. Because you'll need to know what a fast spin echo is and what echo train length means and how we generate that before we can even talk about it. But on scanners, there are still spin echo sequences that don't have an echo train length that are used sometimes. And that is your scan time, TR times next times phase matrix. Actually, fast spin echo sequences are a semi-new creation, right? So talk to techs who've been doing it for like 20, 25 years. They didn't have fast spin echoes when they first started. What else? Do the forum discussions, chat with me, ask questions when you're coming along, when you're coming across them. Next week, we just go over this stuff again. You will have a million questions on the test, so we'll go over the test and solidify this a little bit more, and then we learn rectangular or phase field of view, and that's it. So spend the time working on this, spend the time in the forums. Like I said, maybe 10% of the people get a decent grade on this test. Beat that group. Make that average go up. Spend the time. Nice.
So I just ran it, but I had this, but I
Yeah.
got the answer. I did. I did 5,000.
Really?
I mean, no, but just like 3 or 4 days. I'm just dealing with it. Rest of the week on this guy, they got actually. Oh, yeah.